So welcome back to the statistical learning session. I understand first half of my session, where is the initial 2 hours, I'm sure everyone understood 100% of it. Okay. Second half was a bit confusing. Half the things you would have understood, half things you would not have understood. Going back, I thought on same how to make this much more easy, so that 100% of you people understand what that hypothesis testing is. So what I'll do is we'll focus on this slide, which is the most important, this one, which is the most important to understand. Okay, I have depicted the same thing here. What do we do in a hypothesis? We make an assumption to prove something which is a fact, which may be a fact, may not be a fact, but we are making assumption that what we are saying is factual and we want to prove it. Okay. For example, if I take the process industry example, the dairy milk, the dairy 1 liter pouch being packaged. In that case, system is going okay, but there is a complaints, customer complaints or manufacturer complaints, owner complaints. So the hypothesis is there is a problem with the system, and the entire reason why you are now doing testing is to prove that there is a problem with the system. The objective is not to prove that there is no problem with the system. It is great if you end up saying there is no problem with the system, but the reason of doing testing was to prove that there is a problem with the packaging process. Then we took another example which was of the GNFC urea, new kind of neem based urea I am launching. Now when I am coming up with a new urea, my objective is to prove that the new urea I am making is better than the existing urea. So basically null hypothesis is what it is saying is status quo. Alternate hypothesis is the challenger, which wants to prove the status quo, I have got a better thing which is better than the status quo. So I would, going forward, I would like to implement the new solution which is based on new thing which is proven by my hypothesis test. Okay. So the diagrammatically, we have got null hypothesis, status quo on top. We have got alternate, which is the challenger on the left hand side. Null may be true, null may be false, I don't know. Based on my hypothesis test, I am trying to accept null or I am trying to reject null. So now there are possible scenarios. One is based on my test, based on the evidence that I have collected, the evidence suggests that alternate is a better, that challenger is better than the champion, the status quo. The new thing which is the alternate option that I am suggesting is better than status quo. Okay. Now the question is, at what confidence I am saying the alternate is better than the status quo. Okay. So for that I am doing a test. In that test I am saying I am willing to take a risk of 5%, say alpha. Okay. So if my hypothesis test suggests that alternate is better, in that case my confidence of alternate being better should be more than 95%, that is 1 minus alpha. Okay. So this intersection is saying reject null, which is alternate is better solution, and in fact the true state is that the current status is poorer than the alternate. So this is a perfect outcome for me. But when you are doing this hypothesis testing, what happens? You always do the test with respect to samples. You always do the test by taking samples. Sometimes the sampling may go wrong, right? End of day sampling is always, there is a sampling error. Because of the sampling error, what is the chance of you going wrong? That is, the alpha is what your upfront status, I am willing to take a 5% risk. Okay. So this, when you are hypothesis rejects the null hypothesis in the test, we are trying to prove alternate is better, because whenever you're doing hypothesis test, you want to prove alternate is a better. That's where the alpha comes into play. Is it okay so far? Now let's say take another scenario. My hypothesis accepts the null hypothesis. The hypothesis test accepts the null hypothesis, which what it means is existing status quo is better than the challenger. Okay? If existing solution is better than the challenger, would you go and implement the challenger? No. Do you agree? Would you go and implement the challenger? If you are not going to implement the challenger, in that case, will this error come into play? Because you are not implemented only. Nothing. And that's the reason why beta in hypothesis testing is not considered when we typically do a hypothesis test. Some post-mortem someone may want to do, saying that, hey, my null was accepted, which means alternate was rejected, still I am going ahead and implementing the challenger. Some scenario you may still want to try. In that case, what is the error? That error would say, hey, by going against, I actually was better off. Okay, by going against, actually I would have been better off. So that is typically, but we will not go against the hypothesis test. Okay, that's the reason if a null is accepted, we do not implement the alternate. As such, most of the time in hypothesis testing, we do not focus on this part. And that's why I said yesterday, that beta, in my 15 years, 18 years of career, I have not come across scenario where I was forced to see the beta part. The entire hypothesis testing is focused on this part, this row, this much of the section. Okay? Does that make sense? Is it very clear? So in yesterday's example, when we then took example of launching a product in a new market line, status quo is what? My product is not there. Alternate is I want to launch it. So in that case, what I am saying is, and again see that example, not launching a product in a one market, let's say launching the product in 100 markets. Now if you see from perspective of launching the product in 100 markets, you know if I open 100 outlets, will all outlets work? No. What you are saying is I am willing to take a risk of 5%, which means 5 outlets, probably 1 year or 2 years down the line, I'll see I is making loss. I may end and shut down them. But if 25 outlets are making loss, will it be profitable business? The loss of 25 will eat the profit of 75. You may make net loss. So that's where this calculation, someone was asking yesterday, how do you decide how much alpha you are willing to take? The answer to that is how much error you can go wrong. How much error you can go wrong. Okay?
How much risk
you are willing to take?
I think that's a decision which business has to take.
That is a decision. Now, if we take this example from marketing to say medical science, I am making a medicine. And then I say, okay, hey, I made this medicine. If I give this medicine for a particular ailment for treatment, on 100 people, if you give this medicine, 95 will get cured, 5 will not get cured. Which means, are you taking a decision from a marketing point, or are you taking a decision from a patient standpoint? Now, in that case, if you are taking a decision from a patient standpoint, in that case, what you have to do is you cannot take it 5 people out of 100 will be not cured. You have to build a solution when you have to say 99.99% patient will get cured, 0.01% patient may not get cured. Okay, So in that case, the risk is too high. In that case, alpha has to be too small. Okay. So that's how you have to decide the alpha. With this, is this entire thing clear now? Does it make sense? Because if you don't understand this part of hypothesis testing, because going forward when we see t-test, we see chi-square test, all of these tests are going to give you one output which is p-value. All of the test is going to give a p-value. P-value is probability value. This p-value is always for null hypothesis. If p-value greater than alpha, greater than equal to alpha, accept null, else you may, we typically don't write you reject null, you may reject. Okay.
True versus accept.
This one? This one? True versus reject. Null. Me accept alternate. Null, true, reject, null.
No, challenger is to accept.
Yeah.
As well as null hypothesis is accept.
Yeah.
Both are.
Yeah.
So whatever null hypothesis is like
Null is champion.
there,
Null is
so
champion.
even
This is status quo. This is champion.
this is champion.
Champion, true, challenger, accept challenger. When champion is true, when existing is better off than alternate, and you still go ahead and implement alternate, which means after implementing you will get a poor result compared to what you were getting as on date. Understanding? Which means this is a risk, no? This is a risk. That's what it is saying. Yeah. Clear? Sir, last row. Done? Yeah? So this is the hypothesis test. Yeah? So from that perspective, probably you may now understand the Z test. The test that we did was Z test yesterday. Okay. Let's take this example now. A retailer is weighing strawberry to sell 250 gram punnets. A customer has complained that strawberries he had bought previously were underweight. Customer is complaining that the boxes that you are selling of strawberries, you say 250 gram, but they are underweight. The retailer decides to check weight of 36 punnets. 36 boxes he takes and want to check it. He finds average weight is 248.5 gram and the standard deviation of the 36 samples, that is coming 4.8. In using the significance test to judge whether he is selling underweight punnet, which of the following condition is true? The first three, a significant test is not required. The fourth one is significance test is not required. So solve this problem and tell which is the correct answer.
The weight is 250
Yeah.
250 grams.
Weight is 250 gram is the null hypothesis. How many weight is not 250 gram is the null hypothesis? See, what is status quo? Just think from a retailer point. He is doing the test. Will he be selling underweight? No. Status quo is he is selling 250 gram. So that is mu equal to 250 gram. Now the customer has complained that he is selling underweight. So he is trying to prove that hypothesis. So mu H alternate mu less than 250 gram is alternate. Okay. What is X bar here in this example? Average has come out to be 248.5. What is standard deviation? This standard deviation of the population or sample? 4.8. I have to compute the z score. Z is equal to x minus mu divided by sigma divided by root of n. So where is sigma? This sigma is of sample or population? But what is sigma? Sigma is population, but sigma is standard deviation is available of sample. Now, from based on central limit theorem assumptions, sample is representative of the population. I have taken 36 observations, which is large. The sample has to represent population, and the standard deviation is of the sample, not of the sampling distribution. This standard deviation is of the 36 records. This 36 record is representative of the population. So I can make the assumption that this standard deviation which I have got from the sample is equal to population standard deviation. So I'll say this is equal to sigma. Okay. Please understand there is a difference. Standard deviation of sampling distribution is different and standard deviation of the sample is different. Here we have got standard deviation of the sample. So standard deviation of sampling distribution will be sigma divided by root n. So what is the z coming out to be? Minus 1.87. Now make the diagram. This is right tail test or left tail test? This is a left tail test. So this is a left tail test, which means null hypothesis rejection zone is here on the left hand side, right? Now with minus 1.87, what is the p value?
0.87.
P value is equal to
0.0307.
0.0307.
307.
Okay. What is my alpha? 0.05. Now come to this part of the statement.
If p value is greater than alpha, accept null. Accept null means mu is equal to 250 gram, which means he is not selling underweight. But p here in this case is less than alpha. If it is less than alpha, then reject null. If you reject null, which means alternate hypothesis that he is selling underweight is valid. So at a 5% confidence level, I can say the person is selling
Underweight. Is that logical? Does that make sense? Yeah?
So here the n is 36, right?
Yeah, that is 36. That is 36. Is that clear?
now. Similar to this example, I came across. I'm sure.
Good, yes, sir.
P value z வந்து -1.875 ல -1.875
Population standard deviation. In this case, we do not have population standard deviation. That's why we have taken sample standard deviation as equal to population standard deviation. See, there's a two different word. One is a sampling distribution standard deviation. In this case, the value that I have got as a standard deviation was Punnett number weight 1, 2, 3, 36, and the values are something 248, 251, 250, 249, values. I am computing standard deviation of this. This is given to you. This is a given. I'm not saying standard deviation of sampling distribution. What is standard deviation of sampling distribution? I compute the mean of these weights. This mean of these weight comes out to be 248 point something what is given, right? 248.5. I take another sample of 36 punnet. The mean comes out to be 249.5. I take another sample, it comes out to be 250. I take another 36 samples, I compute 251. I take another 36, and like that I take thousands of samples. And then I take standard deviation of these, that is standard deviation of the sampling distribution. Are you getting? That would be much more lower compared to this. And that is what sigma divided by root n. But here, this is the standard deviation which is given, which is of sample. And here, because we do not have population standard deviation and sample is sufficiently large is more than 30 in this case. Because it is sufficiently large, we are assuming sample standard deviation is equal to population standard deviation. I am not using the term sampling standard deviation. This is sample standard deviation. Okay?
So in case samples are less than 30, then we cannot apply this?
We cannot apply this.
And here we have got sample standard deviation. From here, we actually at the point where we move from a Z test to T test. Actually, what test we should apply in this case is a T test. Because here we have got sample standard deviation, and T test is specifically designed to solve problems where you do not have population standard deviation. You have sample standard deviation and sample is small in size. That's where you apply a T test. However, if you would have applied a T test to solve this, the value of P value would have come very close to this number. But the right test to solve this problem is a T test, because in a T test, the conditions are sample is small, population standard deviation is not available. Okay? But applying a Z test is not wrong in this case. More or less, the T test outcome and Z test outcome are going to be more or less same.
Yes.
Yeah, that was the standard deviation mentioned. That is for the sample.
Yes.
We have mentioned that it is for the 36 cases.
Okay.
I came across a similar example, real life example, but I did not go and do this test. I'm sure many of you, for your kids, and you would have gone and purchased ribbons, laces, because in kids you have got red day, green day, those days. So they, on specific day, the school asks you to wear a red ribbon, green ribbon, yellow ribbon, so they understand the colors. Okay, and for that you would have gone and bought laces, ribbons, those kind of things. So once my wife asked me to get it, I was just coming from office. I said, oh, I'll get it. I went to the adjacent shop and I want 2 meter ribbon. So he removed, and typically, they do like this and measure the length. And the roll that he was having was just completing. It was just, he did like this and then he did like this, it completed. Roll was over. So he gave it to me and said, sir, ये 2 मीटर से ज़्यादा ही है, ले लीजिए. So I thought for a while. He is saying that it is more than 2 meters. And I thought he's cheating. One, he is not doing proper scale measure. And second, because it is exhausted, he's from a marketing standpoint, he is saying, sir, it is more than 2 meters, anyways take it. So I said, okay, 1 meter is approximately 3.3 feet, 2 meter should be approximately 6.6. My height is almost 6 feet. So I said, okay, it's below my height. It is not 2 meter. Sir, no, I said, put it on tape. He realized it was not even 5 feet. Okay. So then I thought this is a very good example. Many places when you go and we shop, they don't use a tape. They simply do like this and give it to us and we buy it. But most of the time, I'm sure if we apply this test, if we buy 30-35 times saying 1 meter, then next day 2 meter, we go for some 30-35 times and take it and then measure it, definitely each time you would be giving some 2 centimeter, 3 centimeter, 4 centimeter less to us. Okay, you can validate with a test. Yeah. Let's take another example. Student t-test. Now we are moving from z-test to t-test. We actually solved a problem where we could have used a t-test, which is the strawberry punnet example. So where is t-test used? It is used specifically for samples where we do not have large number of records. Having said that, t-test can also be used when we have large samples. But specifically why it was designed? It was designed for small samples. Now who designed it? It was found by a mathematician, statistician, William Gossett. Basically, if you go and see the history of this person, he used to work in a brewery by name Guinness. And there they had to create various breweries, so he has to basically that, what do you call it? Barley. Barley is one thing that from which the breweries are made, so he had to do many of those tests. But he did not have sufficiently large number of samples. He had very small samples, because if you are going to taste some food, if you are going to taste some wine, are you going to have thousands of wines and thousands of samples of each wine and then you will come to a conclusion? No, not possible. So you are trying to do some testing to increase the yield, the productivity. Will you have thousands of samples? No, you will have only some 10, 15, 20 options, from where you have to decide which is the best. So he had a specific problem of small data. At that point of time, all other mathematicians who were trying to solve business problems, they were focused mainly on large data. So when he proposed his problem, many of the mathematicians said that, hey, these are very rare problems, so there is no need to focus. But unfortunately, he was having that one of the rare problems. So he definitely had to focus. That's when he created a student t-test. And why the name student? When he did the entire analysis, he could not publish that analysis by his own name. Because in the same organization, some other researcher, he did some research analysis, he published a white paper. Competitor brewery firm, making use of that white paper, they developed own solution, and basically it became, the competition also benefited from it. So the company said, okay, you can publish, but you cannot publish under your own name. So no one will come to know this, where is the application. Okay. So he used an anonymous name, student. And then I think so Fisher, in recognition of the Gossett T, he added student t-test, made it student t-test with some refinements. So this is a student t-test. Application is small samples where you do not have population standard deviation, where you have only sample standard deviation. The key underlying assumption is population is normally distributed. The student T makes the assumption that the population is normally distributed. Okay. So there are different types of t-test: one sample t-test, two sample t-test, paired t-test. So in a one sample t-test, what happens? You got one sample and you are trying to check that sample with reference to some reference point. For example, the example that we did this one, how many samples are there? One sample having 36 records. You are trying to test it with respect to a reference point that is 250 grams. So it becomes a one sample t-test. Two sample t-test, you have got two samples. Two sample t-test, you have got two samples, and now you are trying to prove these two samples are same or these two samples are different. Okay, basically I take two samples from a population. My objective would be to prove the two samples are similar. Okay, in that case you can use a two sample t-test. Getting? And third example is a paired t-test. Before after. ये तो हम काफी देखते हैं न्यूज़पेपर में. In newspaper ad, gym ads, some clinic ads. Before coming to our gym, before coming to our clinic, the person was 110 kg, a fat belly shaped person, and then after 6 months or 4 months, the person became 60 kg, slim and trim. Right? Before, after. Right? Other example, so there are patients having certain medical ailment. Before taking the medicine, what is their various test reports say? BP, sugar, whatever you want to say. After the person keeps taking the medicine for a certain time period, and then you now again see what is the health status of the patient before, after. In a two sample unpaired test, the observation in sample 1 and observation in sample 2 are entirely different. There is not a record which is part of this and the same record is part of this. But in a paired t-test, before, after, the observation which you have before, you are seeing the status of the same observation after. Are you getting the difference? So that is a paired t-test. Yeah. So these are the, after what? After going to gym.
In this case, in the example.
दो एग्जाम्पल दिया ना, पैड टी टेस्ट. You go to gym. Before going to gym, you are 100 kg. Now gym person will make you exercise. They will give you diet plan. You follow that. After that, you become 75. Okay. The entire benefit that has happened is because of your effort. You going to gym, you going to exercise, you regulating your food. But a claim is taken by gym. You don't go to gym, you still exercise regularly and regulate your diet, your weight will still go down. Right? But that is before, after. You have got a medical ailment. A company which is making a medicine, they take patients. They then prescribe patients the medicine, which is typically done by doctors. So that details of the patient before they started taking the medicine is taken. For example, we have a drug, say chemotherapy. Okay, chemotherapy. People who are in stage 1, stage 2 cancer, they, after having the operation done and everything, they go into chemotherapy treatment. Before that, there are certain counts of cancer cells. After taking chemotherapy of 3-6 cycles, what is the count of cancer cells? Is it gone drastically down? If it is gone, which means the chemotherapy is working, right? If it is not gone down, which means chemotherapy is not working. How do you prove that chemotherapy treatment works? Before, after. That is before, after, right? And these are applications, right? So in a one sample test, the way you do is x bar minus x naught divided by s standard deviation of the sample root of n. That is going to give you a t value. Okay. In a unpaired t test, this is some complex formula where you have got mean of A, mean of B, you have got number of observations of A, you have got number of observations of B, basically you have this entire complex formula and you compare the t value, okay, and then you have got a pair t test. Pair t test where you have before and after. In this m is basically the mean and standard deviation of the difference. Basically what it means is, in a pair t test, let's take example of gym only, simple example. I've got 50 people, I've got weights 100 kg, 90 kg, 80 kg, 70 kg, 65 kg, something, and I've got weights after. All of them came for weight reduction. So I have weight before, weight after. I do the difference of weight before, after. There is a difference. That difference I note. I compute the mean of that. I compute the standard deviation of that. That is what it is. Okay. This is very much similar to this. This formula, the above formula and this formula is very much same. Very much same. Right? So this is a pair t test. Okay. Now we are going to solve problems using t test. Only thing is, we are not going to do all of these calculations using some Excel or hand. As we now go into more advanced test, we'll leave it to computer. We'll understand the concept, we'll pass the data, leave it to computer to give the output, and using the output, we'll interpret the output. Interpretation part is still with us. Okay. So let's take the first example. A soft drink filling machine which is in a perfect adjustment fills bottle with 12 ounces of soft drink. If the machine is properly configured, it has to fill 12 ounces of soft drink. A random sample of 49 bottle is selected and contents measured. Sample yielded a mean of 11.88 ounce with a standard deviation of 0.35 ounce. Formulate the hypothesis. First step is formulate the hypothesis. What would be the hypothesis? Null hypothesis and alternate.
12 ounces of software.
Mu is equal to 12. And alternate will be?
Less than.
Either you can say less than or you can say not equal to. Whichever way you want to prove it. Okay. But objective here probably I'll take not equal to or less than. I leave it to you. Depending upon whatever way you do, you have to interpret the values. Now, second step is compute the value of the test statistics, and at a alpha 0.25 left tail, if I take less than left tail, if I say both tail, then 0.05. Okay. At a alpha, we have to decide whether there is a need of configuring the machine or not. Okay. In Python, how you would go about doing it? In Python, how would you go about doing it? First, and I've given this in IPython notebook. So let me just see that IPython notebook is open for me. Yeah, and whether the same problems I have solved here. Mu 1249. Yeah. So I have solved it here. So first I have to take a square root package from math and require the stats package from scipy.stats. Okay. So I require those two. I require square root function from maths package and I require the stats module from scipy.stats. Mu is equal to 12, that is given. Number of samples are 45, 49. X bar, mean of the 49 samples is 11.88. Standard deviation of the sample is 0.35. So standard error is standard deviation divided by square root. Okay. So that I am computing. T-stat is x bar minus mu divided by standard error. Okay. Here standard error has to be computed. Actually it's not standard error because standard deviation is not taken from the population. Here standard deviation is taken from sample, but I am using the term standard error only, is equal to standard deviation by square root of n. So that formula. Degree of freedom, this point I skipped. Whenever T statistics is seen with respect to a degree of freedom. Degree of freedom is equal to number of observations minus 1. Degree of freedom is equal to number of observations minus 1. Okay. So to get the probability value, I take the stats.t.cumulative density function, I pass the t stat and I pass the degree of freedom, I get the p value. Okay. This p value I compare with my, and this p value by the way is a left tail value. This p value is a left tail value. Okay. Can you, someone give me the book? Page number 542. Critical values of t value. Page number 542. On left hand side you see here degree of freedoms are mentioned. Then it gives you cumulative probabilities and then it says upper tail areas. Okay. So now my t value in this case, t stat, I have not printed the t stat, but t stat x bar minus mu is very clear. X bar is smaller than mu, so the t value, whatever value I'll get, will be negative. Do you agree? The formula x bar minus mu. Someone kindly execute and let me know, because in this I think it is not going to execute. Let me. No, don't execute the full, only execute a part of it. Execute only a part of it, only till t stat. What is the t stat coming? I deleted the remaining part. This is not executing and not printing. Oh, I did not. It's executing. Okay, it's executing. Stat, control, enter. Minus 2.39. Okay. Minus 2.39 is the value that has got. So now, if you see this table, it has not given negative values. It has just given all values in the positive. Okay. So minus 2.39, I have to take plus 2.39. Okay. Because it is giving you upper tail test. So I'll assume minus 2.39 as plus 2.39. And now degree of freedom is 49 minus 1, that is 48. So first in degree of freedom, I'll go to somewhere 48. Okay, I come here 48. And then from 48, I'll now try to search where is 2.39 coming. So 2.39, I get here 2.40. This is 2.40. Now I go up and get the probability. The probability is coming as 0.01. No, upper tail we have to take on, sir. Cumulative is, that is the left hand side, but I have to take the upper tail. Okay, it is saying 0.01. Why I have to take upper tail? Because my value is actually negative. Are you getting? Let's understand this. I'll rub this. Is it okay? So they have made this kind of a diagram, and then somewhere here they have put a word T, and somewhere they have put an arrow mark and said this is alpha. Okay, this is the diagram which I have made. What they are saying is, now this table, when I read, it is going to give me alpha value only for this half. My T stat came minus 2.39. Where is minus 2.39? This is 0. So my T stat T equal to minus 2.39 is here. And I am actually interested in null hypothesis. If I formulate, my null hypothesis is mu less than 12 ounce. So it is a left tail test. It is a left tail test. So I am actually interested in this area. Do you agree? But diagram here, what it is saying that the table is going to give you value only for this area. But I know it's a normal distribution. It is symmetric. So minus 2.39, I said t equal to 2.39 for reading of this table. For reading from this table, I said t equal to 2.39 and go and take the corresponding value and it is coming as 0.01. But this is for this area. I'll say, okay, this is this area, but t equal to 2.39, 2 minus 2.39. This is also 0.01. Can I conclude that? Are you all understanding this? So that's why I've taken 0.01 from here, which is actually this. Yeah? So having run the t-test, compare with the alpha. Compare with the alpha. What is the alpha that we have said? 0.025. So what is the conclusion? Is that underfilling or not underfilling?
What is the conclusion?
Underfilling because it is less than 0.025.
Sir?
It's underfilling.
Underfilling, sir? Underfilling. So why underfilling?
Less than alpha.
So you repeat with me.
If p value is less than alpha, which means reject null, accept alternate. In this key p value is 0.01. Alpha we said is 0.025. So p value is less than alpha, which means reject null, accept alternate. Null here was system is working fine, proper 12 ounces being filled. Alternate is less than 12 ounces it is filling. So I accept alternate, which means the machine is not giving me full 12 ounces. Yeah. So that is our conclusion. Do you agree? Null I never said less than. Null is always equal to. Where did I mention? No, see my recording. I am saying I did not mention. Okay. Null is, see, okay. Now, yesterday I did not solve this problem why less than is assumed. Okay. In this case, null is mu equal to 12 ounce, alternate is equal to mu less than 12 ounce. Y is equal to always there. Here, if this is less than symbol, then this will be greater than equal to. Now, why when we write a null hypothesis, why we write it equal to only? Okay. So let us see what is the formula. The T-stat formula was x bar minus, x bar is the sample mean, minus x naught is the reference point, divided by sample standard deviation divided by root n. This is the formula. Okay. Now in this formula, I know x bar. Okay. Now when I say h naught, just hear me out, everyone. If I make null hypothesis, h naught mu greater than equal to 12. Okay. The moment I say this is greater than equal to 12, that is reference point is greater than equal to 12. Now, if it is greater than 12, then I could have written is 11.88 minus 13. I test with 13, no? Why 12? Are you getting? From that point, that's why you have to take whichever is the value closest minimum from with respect to which you want to really compare. At the moment I say greater than equal to 12, you compare with 13, you compare with 14, definitely I am underweight. You compare with 15, definitely I am underweight. You compare with 16, I am definitely underweight. But the point which is closest, with respect to that I want to find. That's why we always write equal to. That's a small subtle thing, but logically when I am testing alternate as less than, really I am speaking the null is equal to or more than equal to. But we don't write that greater than symbol. If alternate would have been greater than, null would be less than equal to. But I don't write less than, because in formula you compare with respect to equal to. That's just a small subtle reason, nothing else. Yeah. Okay, so this is another problem. I'm not going to solve this problem. I leave it as a class exercise. Okay, where again we have to see whether it's a null hypothesis, alternate hypothesis. We have to formulate and do it. End of session, when we get time, all these class exercises which I have left will cover. Okay. Is random sample representative of population? I have a population of 1 lakh observations, and from that population of 1 lakh I take 10,000 observations. Can I say this 10,000 sample is representative of population?
Population is not normally distributed.
I have a population 1 lakh. From 1 lakh, I take a sample of 10,000. Can I say this sample is randomly taken? Can I say this sample is representative of the population? How many no? How many for no?
Why is sample not representative of the population?
The sample size is very less as per the population size.
It's 10%, 10,000.
So, but it should be more than 30%.
I said 30, but never I said 30%.
Sample should be like
वो कल आपको सुपरवाइज लर्निंग में सिखाया था क्या 70-30 ट्रेनिंग टेस्टिंग है ना I got it training testing you learned from there.
It's a subset only. The values will vary, even though it is like.
There is a subset only, then the values will be very.
Values will
You have taken random sample.
Random
You have taken random sample or just?
I have random taken that.
So random sample is always representative of population. That's what you told. It's a only bias.
That is the assumption we have.
That's
Always
what
we
you
are.
have.
Finally, sir has got the point.
Random sample sufficiently large is a unbiased sample. Random means unbiased sample. 10,000 is sufficiently large records. So it has to be representative of the population. I said you yesterday, once data mining sessions will start, you will have a training, testing, and once the training, testing will happen, so I will say I will take a random sample training set and random sample testing set. Then I will say it is representative of population. Then don't spoil my name.
Okay.
I proved with central limit theorem. Definitely there is a sampling error. There is no denying. There is no denying. But random sample is representative of the population. There is a chance event that random sample may not be representative of the population. The chance event is always possible. Chance event can be in last ball you require 20 runs. And the team which requires in one ball they require 20 runs. After you switch off the television, say abhi to haar gaye abhi. Because if say India is playing last one ball you require 20 runs and you switch off the TV and half an hour later you see firecrackers burning everywhere and then you realize hey India won. One ball 20 runs still possible. How? The bowler bowled 3 no balls. Okay. Someone put a towel here. Okay. And you bowl 3 no balls. You can still win. Yeah? 3 no balls, 3 sixes. Yeah, make that assumption. Why 3 no balls, only 3 no balls, 3 runs? But in each no ball you make a 6. Right? Possible. So chance event can always happen. Chance event can always happen. Only thing is you may want to ensure that the chance event is not playing today with us. 99% it is not going to play, but 1% chance is always there. Okay, but a sample sufficiently large is representative of the population and 10,000 numbers is sufficiently large. to a large extent, given 1 lakh, when I compare to 1 lakh, 10,000 is sufficiently large. Okay. This reminds me, I have not did the sampling calculation, sample size calculation. We'll do that. Okay. So sample sufficiently large, and 10,000, 1 lakh 10% is sufficiently large. If this would have been 1,000 observation and then I take 100, then 100 is coming too closer to the 30. Then I would have worried. But it is 1 lakh and 1 lakh 10,000, I am taking 10,000 of it. It's a representative. Now I am going to prove this point. I am going to prove this point, whether the sample is representative or not. Okay. I have given a file, hypothesis test.csv. Just check whether that file is available. Okay. So what I am doing is I have given you a file, hypothesis test.csv. We are just going to import that. This file has got 20,000 observation, and please understand, number of observations are 20,000. So population is 20,000. I am going to take 10% out of it, which is just 2,000. With 2,000, I am going to prove the sample is representative of the population. Okay. So let's import first the packages. These are the packages which I require. This is the import part of the code and sampling part of the code. Sample random equal to 0.1, less than 0.1, which means 10% is what I am taking. Okay. And then I am printing the variables, and the mean of some variables is what I am printing, and doing a test. Okay. Let me just run this piece of code, control enter. It is executing. In this case, what is the null hypothesis?
Sample is not representative.
Alternate is not equal, because that's what all of you raised the hand for, right? That's what all of you want to prove, that a sample is not representative of the population. So null hypothesis, sample mean equal to a certain known mean, because that is the null hypothesis in t-test, right? You take a reference point, and this reference point is basically population mean. Alternate is sample mean not equal to population mean. Now this is an example where, though I am come from a point of view that sample is not representative of the population. I come from this point of view, but my intent is really that this should succeed, right? So we have just imported the data. I've just printed some information, print age, and the details that I have given is the population size is how much? 20,000. Population mean for age is coming out to be 38.9, 39. Sample size is, I have taken approximately 10%. So 2000 observation, 2024 observations have come, and sample mean is come out to be 38.36. Blindly, if I see these numbers, I can say the numbers are very close to each other. There is nothing much I have to do testing, right? But still, statistically, we have to prove. Now, here I am using a t-test. Sample t-test, one sample, because we are doing one sample test, right? I am not still comparing between two samples. I am taking one sample. The other sample is population. I am taking the population mean as a reference point. So I am giving the sample data set age column, and the reference point I am giving is the population mean. With respect to that, I have to do the one sample t-test. I am printing the t-test value. If I print the t-test value, let me run this, control enter. The t-stat is coming minus 0.16 and p value is coming 0.87. P value is coming 0.87. this p value is for which hypothesis, null hypothesis or alternate? P value is for which hypothesis, null or alternate? देखो अभी यहाँ पे कितना आया? T statistics minus 0.16. I'll take it as 0.16 and the degree of freedom will be very high. Degree of freedom will be 2023. तो ये तो आएगा नहीं इसमें से, ये टेबल में से नहीं आएगा. P value is always for the null hypothesis.
No, but P value is more than P value alpha.
P value is always that you get from the test. P value always come for the null hypothesis. That P value you always compare with the alpha. So my alpha, typically what we set is 0.05. P value has come out to be 0.87, which is way above 0.05. Which means I've got 87% confidence that null hypothesis is right. Only 13% is the confidence that sample is not representative of the mean. 1 minus p value is for the alternate hypothesis. So only 13% confidence that the sample is not representative of the population mean when I compare it based on age. So beyond doubt it is proven that at least on the age parameter, sample is representative of the population. Right or wrong? It's above 0.05, no? Okay, na? Now let's do the test for another column. Score. Yes, sir?
Can you conclude that example? Sorry, result?
The p value is above 0.05. If p value is above 0.05, accept null. And null hypothesis is sample mean equal to population mean.
So here the assumption is alpha is 0.05. Okay.
Yeah.
Okay. One, I just executed that previous code thrice. I am getting the.
It is different values alpha, no? See, please understand. Please understand. You are doing different sampling. Each time you run the code, you are doing different sampling. But each time you are getting the p value above 0.05, no? So each time we conclude the fact that. Each time we are concluding the fact that sample is representative of the population.
And what about the confidence percentage? Like you're talking about 87%.
See, here when we are accepting a null, we typically don't want to go into confidence percentage. Confidence percentage is always for the alternate. Okay? Confidence percentage is always for the alternate. But here I can say 87% is the confidence where with which I am accepting the null. Because the value is too high. Okay? That is what I can say.
Yeah?
So if we switch this hypothesis, how will we go?
We cannot switch the hypothesis.
The framing of the hypothesis will always remain same.
Because yesterday in the machine learning session, he was saying that the null hypothesis is that our model does not match the real world, and the alternate is the model matches the real world population. He was saying.
No. He was saying the null is what the situation is currently.
Which is the real.
Which is the real life situation. If I'm trying to understand from the perspective why am I building the model first of all, I'll build the model to prove an alternative hypothesis. So my model is my alternative hypothesis.
Model is the alternative.
That's what he was saying.
Okay.
So what he would be saying is null hypothesis is a status quo. Without model you are running the business. Alternate is with model you are going to run. Alternative is with model you will run better. That's why you want the alternate to succeed. Okay?
So here, this is one sample test and population mean is the reference point you have taken.
Yeah.
Because one sample you require a reference point. So if you repeat this test, which the code I have given, anyways I have put all of that in my slide. So if you repeat the test, you will realize that the test is working fine across parameters. Across parameter.
Because each time the sample is different, you are getting different values.
That is okay. See, each time you do sampling, you will get a different sampling. But the point is, each time you are doing sampling, more or less you are saying that sample mean and population mean is equal. That's the more crux. There is a crux. Okay. So a sample which is sufficiently large, it is representative of the population. How many of you agree with that statement? A sample which is sufficiently large, it is representative of the population. How many of you agree with the statement? Random sample which is representative. Okay. Okay, so all of you agree?
Okay.
So that's why you do now. Okay, now coming to the error part. See, definitely when you do a sampling, you may have error. Okay. Now assume, let's take a simple example. You learned supervised learning, right? Supervised learning is typically used to solve a problem of 1, 0. There are two classes. Most of the problem statement are 1, 0. So now assume, what was the example you took yesterday? What was the business case? Breast cancer or what? Breast cancer, malignancy of the malignant or not malignant. What percentage of data was malignant?
No,
Benign
was
40-60. Okay, 40-60. Okay, assume the 40% was benign, 60 was malignant. That was the proportion. Opposite, kuch bhi chalo. 40-60 was class A and class 60 class B. Now when you do sampling, it may so happen if the data is not large, okay, because in these kind of cases you will not get 20,000, 20 lakh, that kind of observation, you will get 2,000, 5,000 observations. So assume your data is only 2,000 and from that you are taking some 1,500 observation for building your model. It may so happen that 40-60, which was proportion, may become 45-55 in a given sample. Now 40-60 becoming 45-55 is a huge difference. But because of sampling error and small base, this can happen. So when you are doing these kind of things, what you can do is, when you are taking a sample, you take 1 or 2 parameters which are very critical for you from the entire analysis point of view. That 1 or 2, either you see the numbers, 40-60, I got 41-59, go ahead, don't bother much. Okay, my approach is, I see 1 or 2 critical variables, I see what is the proportion or the mean of those critical variables and take a call. I don't even go into these t-tests. And if you feel that, hey, someone want to be much more statistical, on that parameter, you apply a test and say the sample is representative of the population. On that 1 or 2 parameter, you can apply, right? And ensure that training and testing data sets are now completely representative. But typically when their samples are too large, we just see the proportions, 1 or 2 critical variables move forward. If it is more or less in line with what is the population parameter, we don't even bother about the test. Okay. Now coming to an independent t-test, 2 sample. A principal of a school is interested in testing whether average number of hours studied by a boy is significantly different from the average number of hours given by girls. So he want to do a test, a sample of 15 boys and 15 girls, and the study hour is collected. 2 samples have been drawn independent of each other. One of the most important element in t-test is the sample should be independent of each other, which means in an independent t-test, observation which are in sample 1 are not there in observation in sample 2. Because it's an independent t-test, it's not a paired t-test. Okay. The data collected is given in student study hours.csv file. Analyze the data and determine whether there is a difference in the mean study hours of boys and girls. Use alpha is equal to 0.05. So what we are trying to prove is, are boys studying more or girls studying more? Okay, or both of them devoting more or less equal number of hours, is what we are trying to do. So the file is given in student study hours.csv. I am just importing the file and doing a describe. If I import the file and do describe, this is the outcome that I get. So here we can clearly see the mean hours of boys is 7.4 and the mean hours of girls is 7.9. So relatively we can say girls are devoting more time by seeing that data. But is this difference of 0.5 statistically significant? Is a point. Okay. So now to do that we require a t-test. Now one of the important element in a t-test is the sample should be normal distribution. Okay. So here what I am doing a histogram plot to see whether the graph is normal distributed. If I can F11 full screen. Okay. It seems like a bell curve. The graph seems like a histogram seems like a bell curve. Okay. So I say okay, it's a normal distributed. Okay. The other approach to say whether data is normal distributed or not is by running a QQ plot. There is something called QQ plot. QQ is quartile. Okay. So if in a QQ plot, this quantile, theoretical quantiles and sample quantiles, it is putting it, if this goes as a straight line, if this graph looks like a straight line, in that case it's a normal distribution. Okay. So here if I have done, here I have shown one way of proving a normal distribution, which is using a histogram. For boys I have done histogram, for girls I have done a QQ plot. Okay. Two approaches I have explained. Dots are the data points. The theoretical quantiles and the sample quantiles. Sample data is converted into quantiles and then you are plotting a quantile versus quantile. That's why QQ. Okay. How the calculations are done for quantile calculations, I am not going into that. But theoretical and these quantiles are done and then you are plotting them. It should come a line at a 45 degree. Okay. If line comes at a 45 degree, which means it's a normal distribution. Because line will come at a 45 degree only when things are exactly at a 45 degree with a theoretical. So it is coming more as a straight line. It's a normal distribution. Similarly, I have done it for boys here bottom. Okay. Code running, code is all given here. You can run the code. I am not running it because the output is directly on my screen. Okay. Then you will have to apply a independent t-test with a not normal variance, not equal variance. So there are some other tests, variance of that test. Okay. So the other way of proving normality, if someone does not like to go through a histogram or a quantile plot, then I can apply a Shapiro test. Using a Shapiro test, null hypothesis, it is not normal, alternate is normal. Okay. So applying a Shapiro test where I am using SciPy stats package and Shapiro the function from that package, I apply to the data and I get an output. P value is coming as 0.587, which means reject null. Null hypothesis for the Shapiro test is, and all these things you may not remember. So what happens is you go to a document, okay, where I have clearly written what is the null hypothesis of that test. So here it is for the Shapiro test, the null is not normal, alternate is normal. Okay. And what you are trying to prove, again if you see, you are trying to prove it's normal. That's why you are running the test. So from that p value, it says okay, p value is 0.587. Again the test is saying it is normally distributed. Similarly, I apply the same test for girls, it is again getting normal. All these tests why I have done, why I have come across these tests, reason is one of the strong assumption of the t-test is the population is normal distributed. So how to test normality is what I have explained here. The four ways I have, 3 ways now I have explained. One is a histogram, just see the histogram, it's a bell shape, normal. See the QQ plot, if it's line going at a 45 degree, normal. Shapiro test, the other test also, Bartlett test, Lenivo test, something, Levine test. Okay, those tests are what we also see going forward. But here 3 ways is given. Okay, Levine test. Levine test is okay, not for normality but for equal variance. One more assumption that independent t-test makes is the 2 samples that I am having, the variance of them is equal. The variance of the boys and the girls, the sample A and the sample B which I am comparing is equal. If it is equal, then you can use a t-test with equal variance. If it is not equal, then you have to use a t-test saying that variance is unequal. So it will have some adjustment factors. Okay. So here my Levine test is saying that the variance of these 2 are equal. Not equal variance, alternate is equal variance. I get a p-value of 0.46. I can see what is the standard deviation is 0.82 for boys. Standard deviation for girls is 0.68. More or less it seems to be close to each other, but how close they are I cannot judge. So I am going through a test route, and the test route is saying 0.46. 0.46, that's why I accept the alternate, and alternate of the test is equal variance. So I can say that 2 data points that I am analyzing, they have equal variance. So if it is equal variance, in my independent t-test, I'll say equal variance is equal to true. If the variance would have not come equal in that case, I would have said equal variance equal to false. The test internally would have taken the adjustment for not equal variance.
Are you getting?
Please can you go to the previous p-values? There also we had 0.45 and 0.55, right? So in this case also we are accepting the alternate.
Yeah. Your alternate is normal and I want normality.
Okay.
Right?
So having gone through that, I now use the t-test independent. IND is independent. Earlier was t-test one sample. It was t-test one sample, something, right? This t-test one sample, because it was one sample. Now there are 2 samples, but these samples are independent. We are not in pair t-test. So we are now using a formula t-test independent.
Here, accessing the null hypothesis, right? Here it is mentioned in the comment saying that failed to reject the H0. That means we are accepting the H0, right? As it is normal.
This one? Conclusion, are you going to conclusion?
Normality test I'm talking about. In the comments it is saying that failed to reject H0. That means we are accepting the
Normal.
That means we are accepting the null hypothesis, which is normal, right?
We are accepting the alternate.
Alternate is the normality.
Fail to reject H0.
H0 is the null hypothesis.
Null hypothesis is not normal.
H0 means representation of null hypothesis.
H0 is representation of
So
normal.
failed to reject null hypothesis. That means accepted the null
Alternate.
Alternate. It should be rejected.
No, this is the statement. This is
Fail to reject. See, that's what I said. See, when I wrote that yesterday, I would have noted here, if H0, if p value greater than alpha value, accept null hypothesis. Okay. If p value less than alpha value, we may reject null hypothesis. Yesterday also I specifically said the word statistically, that's how you write it. We may reject null hypothesis. We don't say we accept alternate. Okay, that's a statistical way of saying thing. But the right way, layman way is, that's what I learned. I also learned, I'm not a statistics student. I was doing a training in one of the consulting companies. And statistics, half the people who came from induction purpose, they were engineers. And there were 3-4 statisticians from DSC, Delhi School of Economics and other things. So I was teaching stats, and anyways, understanding hypothesis test is not an easy thing. So after doing all of that, I said, I'm going to now give a layman approach of understanding. You get a p-value. That p-value, what you said, say, if p-value is coming, say 0.03, then you should say, At 3% confidence, I accept null hypothesis. 1 minus alpha is for alternate. And at 97% confidence, I accept alternate hypothesis. And now this 97 is above your benchmark of 95% confidence. So you go ahead and say, I accept alternate hypothesis. So someone from Delhi School of Economics stood up. Sir, this is a wrong statement.
I said, I know it's a wrong statement.
What they say except, like,
I said it's very easy because both the place I said accept. At 3% you accept null hypothesis, at 97% you accept alternate. I said I know it's wrong, but I'm with a layman language it's become fail to reject, may accept, become complicated. So I said I'll go with a very simple layman language. 3% accept null, 97% accept alternate. Now choose among the two which you want to go. It's very logical. 97 accept, it is more above my benchmark. So that's why I was very statistically correct. So when I'm writing this statement, it's much more statistically correct. Fail to reject. Okay. This fail to reject null meaning accept alternate. Okay. May accept alternate. May accept alternate. Okay. तो ये निकाल देता हूं मैं, बट इसका मीनिंग ऐसा है. Okay. So I hope what I've shown on the test codes are, first is you have to test for normality, you have to test for equal variance, Shapiro for normality, QQ plot for normality, histogram for normality. 3 ways I have given. Leave-in test for equal variance. Okay. Having done that, I now apply the t-test independent. I give the girls data vector, I pass the boys data series, the 2 series of data. Okay, I pass that and I say equal variance. It applies that and it gives me p value 0.08 at an alpha of 0.05. Null hypothesis in t-test is mean A equal to mean B. Null hypothesis in t-test.
Okay, but you're not accepting this.
Null hypothesis in mean A. So mean A is mean girls, mean hours given by girls is equal to mean hours given by boys. Alternate is mean hours given by girls is not equal to mean girl. Okay, that's our alternate. P value is coming out to be 0.08. I want to test it at alpha of 0.05. P value is greater than 0.05. So I accept. If P value is greater than for alpha, accept null. If P value is less than alpha, reject null. So here P value is greater than alpha. So I accept null hypothesis, which means mean hours spent by girls for studying is equal to mean hours spent by boys. So here from the outcome, you see those girls gave 7.9 hours, boys gave 7.5 hours. Visibly 0.4 was the difference, but statistically 0.4 hours is not that significant a difference. And logically, if you ask me, say 8 hours is what girls spend and 7.5 hours is what boys spend, and the difference is half an hour. Okay. In 8 hours, that half an hour is 5%, less than 5%. Girls are spending only 5% more time, right? Approximately 5% more time they are spending. Someone spending 5% more. It is statistically different. Not. It's trying to just validate that, hey, half an hour difference is not a significant difference between the spending time, is what it is trying to say. Okay. All the codes are given. I want you to execute the code and run all of the codes. Because I have not been running because my output was there, but you run the code so you will get the confidence, I have executed the code, right? Otherwise that confidence will be low. Otherwise what will happen, someone will say sir ne Python code run nahi kiya, right? Because all of you are for AIML, no? Many of you would have joined AIML with the assumption machine learning is advanced programming, and the programming part does not happen, then they will feel that they have not done something was missing in the session. So machine learning is not advanced Python programming, huh? But yeah, you should get the feel that we have executed in the session. So that's why I want you to execute. Then you make unequal. In that formula, make it false. There is some variant of that formula will get applied.
One question. In real world, when you execute any project, when you execute any project for ML or stats, who decides the confidence level? Is it business head or you?
Okay. So
When we execute the projects, and most of the projects where we execute, I have used logistic regression. In logistic regression, when we build models in industry, the benchmark alpha is set as 0.0001. Alpha is set as 0.0001, not 0.05. So whenever I get any variable, saying this variable helps make the prediction better, I take that variable only if it comes at a significance of 0.0001, which means 99.99% confidence level.
That means accuracy.
Confidence level is not accuracy.
these are two different concepts. Okay. The Colgate evidence of 99.99 it's not accuracy, but it's confidence level.
Yes, you got the point.
But does not it change from business to business or the line of business to line of business?
Obviously, that's why you have 6 sigma, right? That's why you have 6 sigma, right? So in medical industry, you may want to go from 99.6 sigma is 0.60 and 1.
Yeah.
Right? You have that 6 sigma.
There it is accuracy. In the medical domain.
See, when we get parameters into a model, never it is accuracy. But yeah, the final test of the medicine is based on something called as sensitivity and specificity, which is part of accuracy matrix, confusion matrix or classification matrix. Final test of the final model. See, our model is built a sum of many variables. The variables we get at a 99.99% confidence level.
Because in many of the problems that we would be dealing going forward, the alpha would not be like given straight away.
In that case, you use in industry, as I said, 99.99. So you don't even have to bother about that. You will have to take that.
Okay. All of you executed the code?
Yes.
Yeah. Done.
For every project, so for our model is 80% is accurate. So on top of that, we capture 99.9.
Wait. See, there are two elements. One is the confidence of the variable. That is what we are doing here. Whether that variable is what it is saying is. Wait. Let me take a simple example to explain this thing. What is accuracy and what is? I want to say based upon attributes of a human being, I want to say whether it is a male or a female. Okay. So I give one attribute which is say length of the hair. Okay. So length of hair, and say if it is greater than 2 feet or say 1 feet, I say it is female. and if it is less than 1 feet, then I say it is male. That's my model. Okay, a very simple model. If I take a data, will it not come significant parameter to get the gender of the person? Will it not come significant? It will. But will it be 100% accurate? No. So basically if I classify based on this, then actual gender and model gender. Female, male, female, male. This is correct prediction, this is correct prediction. These are wrong predictions. Sum of wrongs divided by total observation is accuracy. That is accuracy. Okay? And what is confidence? That if I use this parameter to distinguish between the two gender, will it be able to distinguish? Yes or no? Yes. How confident is I am with the attribute? I am 90% confident, 95% confident, 99% confident. That is the alpha value. That is for the attribute. Okay. Confidence does not translate into accuracy. Confidence does not translate into accuracy. Because if I do at the variable comes at 99.99% confidence, okay, despite the variable coming at 99.99% confidence, you will see accuracy coming at 80% only if you really do this experimentation. Okay, what it means is the variable can help predict gender, but it need not mean 100%. Let me take another example. I do a marketing offer. Typically, if I'll ask you, how many of you, I give you offer as a bank, you get messages, right? I gave you a message saying that, hey, we are giving a personal loan at 10% rate of interest, processing fee waived off, no documentation required. How many of you want to take the personal loan? अरे कुछ भी document नहीं दे रहा हूँ, 10% rate of interest दे रहा हूँ. Why are you not taking personal loan? I am a Kotak Bank, say, I am a ICICI Bank. Okay, I am Kotak Bank. I sent that offer. How many of you want to take a personal loan? You take 2 people. Now he is genuine. Then okay. 2 people want to take. Why all of you are not taking? Huh? अभी तो इतना फीस भरा है ना, कैश फ्लो बहुत है, फीस भर दिया फिर भी कैश बैंक में पड़ा है, ले लिया क्या? Okay, so only 2%. So typically when you do these offers, what happens? 2% people take the offer, which means I am sending offer to say 10,000 people, 200 people would take. Okay, which means I now build a model. The entire objective is to build a model so that I can better identify, instead of targeting 10,000, can I get that 200 by targeting only 500? Now to identify the need that these people require personal loan and these people don't require personal loan, I would identify some parameter, say bank balance. Low bank balance mean higher requirement of loan, high bank balance means no requirement of loan. I make will this parameter come significant in able to distinguish the customers who need loan and who don't need loan? Yes, it may so happen many of the people who have low balance, does it mean all of them will turn up and take the loan? No. So assume you build a model, 10,000 people, let's say, just put it into 2 buckets, 5,000 low balance, 5,000 people have got low balance and 5,000 people have high balance. 2 segments, simple. Take loan, yes, no. Based on hypothesis, what you are saying, low balance people will require loan, high balance will not require loan. That's the hypothesis. If you run a test, will the variable come significant? Will the variable come significant? Yes, it is going to come. Why it will going to come? Because you will see when there was 2%, in this segment probably this is 4.5%. In this segment it is 4.5%, and in this segment it is just 0.5%. As such, this variable is significant to distinguish between the two categories. But now, of the 5,000, if 4.5 is taking loan, which means 5,000 into 4.5, that is 4.5, 9, 18 and 22.5. That is some 22.5, and because it's 12.5 people would take loan. Right? Remaining 0.5, that is some 25 people will take loan. Here. Something like that would be the distribution. This is 5% we have taken, 1125, and this would be 250 something. I have not taken it 10% something. But this would, remaining people who are not taken loan. Now, what is my accuracy? I said all of high banking, high balance should not take loan, and these I said should take loan. Yes, yes is my correct. No, no, no is my correct. But this still, some of the high balance people ended up taking loan. Many of the no balance did not end up taking loan. My accuracy is still not 100%. It would be low. Are you getting the maths? So confidence is one element. It is just saying the variable is significant or not. Overall outcome is the significance of the accuracy of the model. So don't relate high confidence means 99.99% confidence means 99.99% accuracy. These two are different metrics.
So in the real time, to get to analyze the confidence of the teacher to put into that model, so we'll calculate the confidence, right?
Confidence is to say whether the variable should be part of the model or not.
But is it always we calculate for all the variables or from domain?
All variables that are going to be part of your final model, if you are using a regression technique, you have to ensure it satisfies your alpha threshold criteria.
So this has to be part of the confidence. Finding a variable significant.
Variable is significant or not, has to be.
Every variable.
All variable that comes in your final model has to come statistically significant.
Okay.
So sometimes you know like and go with some kind of intuition from the domain knowledge. I know that these variables will be significant and going.
Can you repeat that statement?
Suppose I have a huge
Here, so everyone can hear.
Yeah, so sometimes if the variables we know like beforehand like from intuition that we have to take this variable and I don't want to find the variable significance. Say I have 2000 variables, so I don't want to.
So you want to go by intuition.
Yes.
The answer to this question is, why are we doing hypothesis test? We do hypothesis test because we have an intuition. That is hypothesis. Intuition is hypothesis. That intuition we validate with data. Now, having intuition does not mean that is a truth. That intuition, when validated with data using hypothesis test, validates whether the intuition is right or wrong. So, making it is like saying that I learned statistics and then I am going to go with intuition. I learned analytics, then I'll build model only by intuition. No, the intuition, if it is really genuine, it has to come through statistical route as significant. So I will not answer this question, hey, you have got intuition, but it is not coming statistically significant, still get that variable in model. No. So coming back, so don't confuse confidence with accuracy. Yeah. Pair t-test. Okay. So here, student score data before and after the module was taught is given in a file studentscore.csv. So basically, if you are going to have a lab assignment, right? So this lab assignment, if Edwin or whoever is going to conduct would have taken that lab assignment before my session, then you would have been graded. And After my session, the same lab assignment is given, and then similar lab assignment. If I give same, then what will happen? Someone would have cracked it. All of you would have known the answer. Similar lab assignment is given. You have before and after scores. Now, has the training, has the teaching helped or not, is what we are going to see. So, this is a paired t-test, because you have now a scenario before and after. Another example is, see, concrete blocks. So, you pour the cement and then you let it set. Okay. Now, once I have poured and then I am allowing it to set and then I use it. Okay. So, that entire process. If I pour and then I see the concrete block after 2 days, there will be certain amount of strength that concrete block would have generated. So, I allow setting process to happen only for 2 days. Or if I see the block after 7 days. So, one incidence is 2 days. Say, second is the same block I see for the strength 7 days down the line. I take a block, certain 50 blocks I have, pouring done, setting done. After 2 days, I see the strength. After 7 days, for the same block, I see the strength. Okay. Again, this is a before after. After is after 5 days, and before is on second day. Can I do that? So, again, this, what is the objective of this kind of a test? The objective of this kind of test is to see whether we should allow it to set for 7 days or whether we should allow it to set only for 2 days. If it happens in 2 days, my productivity will increase, right? But if I have to give 7 days, which means I require more space to keep them, right? So, if my work, I get the same strength in 2 days as compared to 7 days, I would have done that only in 2 days. But if I don't get the same strength after 2 days as compared to 7, I'll have to let it settle for 7 days. As simple as that. So, again, before, after, right? So, these are applications. So, here I have taken a simple example because this we can very easily relate. My scores before, after, my weight before going to gym, after going to gym, my medical reports before taking the medicines for my ailment, after taking the medicines. Okay, all these are applications. So, I have given 2 data sets, a student score where there are 2 columns, before and after. If we do a descriptive statistics, we see mean is coming 18, the score after the training is coming 20, not much difference. But is this difference statistically significant is the question. Visibly, I feel 18.2 and 20.5, not much, right? But is it statistically significant? Visually, descriptive stats, how do you present this information? Using a box plot, okay? So, syntax is given, box plot, syntax is also given. Check for normality. Once again, t-test applies when data is normally distributed. So, Shapiro test, it does not seem to be a perfect normal, but still I'll assume it normal because the p-value is saying it is normal, okay? If I would have gone with a histogram, probably I would have concluded it is not normal, right? But the p-value is saying it is normal, so let's assume normal. This is a relative test. T-test, one sample, t-test, independent, t-test, relative. Now, because you are seeing the same data, relative. So, t-test are real. I give after, before, the 2 information is a 2 sample outcome and the p-value is coming as 0.002, which anyways from the score was not much different, but here I get a p-value which is 0.002. So, what do I conclude? Is there a significant difference in score before after based on statistical test, or there is not much significant distance in score? P-value is 0.002. Alpha is 0.05. We reject the null and accept the alternate. And reject null means in t-test null is PA equal to PB. Mean A equal to mean B. Alternate is not. So there is a significant difference. So that's a conclusion. How we could have done the same calculation different way? The data is of the same samples. Data is of the same sample. So what I can do is first compute the difference. The moment I compute the difference, mean becomes 0. If there is no difference, my mean should be 0. The two sample paired sample become one sample t-test. Are you getting the point? That's what I explained when I gave the formula. Yeah. M is the mean and S is the standard deviation of the difference D. The moment you compute this becomes a same formula. In this formula, x naught is the reference point. The moment you compute the difference, x naught reference point becomes 0. Right? X naught reference point becomes 0. So this formula writing as m minus x naught is 0. This formula and this formula is same. So a paired t-test can be converted into a one sample t-test, and that's what I have shown how I can do the same calculation. I do a difference between the pair and then apply one sample t-test. I get the same p value.
So your reference point is 0 because you are actually.
The assumption is
Null hypothesis assumption is sample A equal to sample B. That is the null hypothesis. Sample H naught is sample A mean equal to sample B mean. Sample B is here A before and A after in this case, right? Do you agree? This moment I move it to left hand side, it becomes sample A before minus A after equal to 0. That's why H naught becomes, mean becomes 0.
What are the hypotheses here, the levels? Because you have taken a test, you can assume that after taking the test, the mean has to be higher than the before. So can't I assume that that's the hypothesis?
So now if you want, the difference will be more than 2 levels. There will be more, the difference will be, you assume, do to hoga, a score increase of 2 will be there. If a score increase of 2 is there, I assume it is no difference. Because marginal improvement will happen. As I said, in this, frankly speaking, if 18.2 and 20.5, there is no use of that training. Then only marginal difference has to come. What I could have done, when I convert this into one sample, what I could have done is, I would have said score A after before minus 2. I add one more element, minus 2. Now still mean is 0, because I have already said a minimum improvement of 2 points will happen. For me, if the improvement is more than 2, only then it is a significant improvement. Only then the training is significant. So I add that minus 2 factor. Automatically again mean goes down to 0, no? Because you are now taking with respect to 2. Does that answer your question?
Is it obvious that difference lead to 0 or?
See, that's what I am answering. The objective is, see, you go to a gym, as I was saying that, hey, you go to a gym, you follow a diet plan, you follow the exercise regime, automatically you will lose weight, right? You don't follow, you are not going to lose, right? Now, which factor is under the control of the gym? The exercise. Because if you come to exercise regularly, we will know you are doing exercise. But the diet plan, whether you follow or not, I don't know. Okay. Now, but I want to take benefit of both the elements. But one element is not in control. So instead of saying because of my gymming and diet plan, 5 kg is what is lost. So my target is 5 kg. Okay. So I can do that calculation before, after, and minus it with 5 kg. The mean will now come down to 0. So I can take that as a reference point. So that adjustment what you are asking, you can do in this formula. Straight away you take that adjustment factor here and make it as a one sample. Done. Right or wrong? Yeah. So that is, this test is specifically designed to say there is a difference between the two numbers. But if you are not happy that two numbers are definitely different or not, you want that, hey, it should be at least this much is bare minimum I am expecting. If it is above that point also, then I will say it is. You put that factor, adjustment factor, and make it one sample t-test, go ahead and do the test. Yeah. So if distribution is not normal, if the distribution, the t-test makes use of the fact that the distribution is normal. However, if distribution is not normal, a variant of the t-test, which is a non-parametric test, which is called Wilcoxon t-test. I have not highlighted parametric and non-parametric. So now I'll just highlight the term, because if I would have highlighted this parametric and non-parametric term very beginning of the session, we would have got confused. Tests are classified into two. One is called a parametric test and second is non-parametric test. A test which makes use of mean and standard deviation, that is called parameter estimates. A test which is making use of mean and standard deviation as part of the calculation are parametric test. A test which is not dependent on mean and standard deviation is called non-parametric test. Okay. Typically in a non-parametric test, what happens is you convert the numbers into ranks. You convert the numbers into ranks. And then based on a ranking position, you do the test. That's how a non-parametric test works. So more details you can go and search, but what I am trying to say is the data point is converted, for example, scores of the student. In that case, score is absolute number. But what I can do is, based upon the score, I can say this is rank 1, this is rank 2, this is rank 3, rank 4, rank 5 in the class. And then I use before rank, after rank, and then do the test, compare the results. Those kind of tests are called as non-parametric test. Because in that case, you are now not dependent on mean and standard deviation. Okay. So we have completed t-test. Let's quickly take a break. All of you, I hope you are able to follow. Lots of statistics is being bombarded, I understand. All of that you may not completely understand in one go. You may have to see repeat videos. And this book, I have seen that this book is really good. So do refer the book, try to solve some problems. I would advise that solve at least 2 to 3 problems on your own, or solve the solved problems on your own and see the solution. Once you do that, that is sufficient to understand hypothesis testing. That when I was noting here, I wrote here fail to reject H0, and I said meaning except alternate. We are saying fail to reject null, meaning except null. Sorry for that. And null hypothesis in Shapiro is basically it's normal distributed. And reject H0, meaning except alternate. Okay. So So this is a correction. So when you see the video, the second part we have corrected. Okay, is that okay? So let's move on to our next stats test, which is ANOVA. See in a t-test, what you can test is one sample with reference to respect to a reference point, or you can have two samples, or you can have two samples which are paired. But the moment you have to go from two samples to three samples or more than three samples, you cannot use a t-test, because t-test is max for two samples. And what does t-test prove? Whether the means of the two samples are equal or not equal. That's what the t-test is. If you have more than two samples, then you have to go to ANOVA, which is analysis of variance. Okay. This is what I've said. T-test compares mean between two samples. What if there are more than two samples? And that's where ANOVA comes into play. What we are going to discuss is one-way ANOVA, which means we are just changing one parameter to test whether there is a impact or not. I'm not sure, but why I feel that during my school days we had this ANOVA thing taught, or probably junior college it was taught, and that time we had this one-way ANOVA. Probably you would have also been learning this, and there would be one example which typically is given to teach ANOVA concept, and that example is typically given is, and this is also used by the way in design of experiment. The extension of this is design of experiments. Say you got this farm, you have this farm broken into many elements. Now you are trying to test fertilizer. Fertilizer has got, say, composition A, B, C. These are different compositions. So you say this is 60, this is 20, this is 20. So you may have one experimentation happening here with some combination. Then you may have different composition happening. You try that 60, 40, 0, something. And you have various combinations, and then you try to see where the yield is coming higher. Okay. And based upon where you get higher yield, you try to find out which composition, because you cannot try all possible composition. Basically, you cannot try 59, 19 and 22. You cannot try that. You have some combinations you can do and try it out. And then based upon the various yield outcomes, you determine what is the optimum combination of the three. That is entirely something called design of experiments.
It's like randomly.
That is, yeah.
Just like randomly.
Yeah, basically there is a proper science to it.
Oh.
To create various combinations such that by using all the outcomes of different combinations, so basically if this is a grid of 6 by 4, 24. So here now you have got 24 outcomes coming. And then you will have 24 equations. Why? Because there is a, B, C equal to yield. Right? And then using those combinations, you may solve the equation and then find what is the optimal of A, B and C. These are all optimization problems. These are all optimization problems which are part of design of experiments. However, we are going to take a very simple approach, which is a simple one-way ANOVA, okay, which is analysis of variance. Here only one parameter is changing. Here only one parameter is changing. So in a one-way ANOVA, what we have is simply, I got say fertilizer X, fertilizer Y, fertilizer Z. Okay, and here probably there are many experiments happening, so that finally I get the mean standard deviation of this. Here there are many experiments happening, I get mean standard deviation. I hear many experiments happening, mean standard deviation. Once I have got the mean and standard deviation, that is variance, square of standard deviation, mean and variance I have got, then I will have to prove whether there is a difference in mean of these groups, whether there is a difference or there is no difference. Okay. Null hypothesis are all means are equal. Null hypothesis in ANOVA is all means are equal, which means outcome of fertilizer X, outcome of fertilizer Y, outcome of fertilizer Z is same. Alternate hypothesis is mean are at least one of the mean is not same. Alternate here is not all means are not same. The null hypothesis, alternate hypothesis is framed as at least one of the mean is not equal. Are you getting? So we are in a one-way ANOVA. We are in a one-way ANOVA. If you change more than one parameter, it becomes two-way, that is MANOVA, multi-way ANOVA. Okay? But for us, one way is good enough to learn, and then depending upon your problem statement as and when you face, you may go into multi-way and all of those things and design of experiments. Null hypothesis, alternate hypothesis, which I just framed. Is that clear? Yeah. One way ANOVA is a omnibus test statistics. What it means is, when I apply a ANOVA, it will prove either all means are same or all means are not same. But it cannot tell me which of the mean is not same. It will not give me that outcome, because end of day when you run this, it is going to throw a p-value. It is going to throw a p-value, and that p-value interpretation is at least one of the mean is not same. Which one is not same, which one is higher, which one is lower, you compute the mean and get that outcome, right? Or there is a test which you can run to find between pairs which of the means are not significantly same or different. Okay? To determine which specific group are significantly different from each other, you have to apply a post-hoc test. Okay? So if you want that further, that is called Tusky, I don't recollect, Tusky test something. Let me just see. Yeah, Tusky HSD test. That is a post-hoc test you have to apply on the same data to then get which of the means, which of the pair, whether fertilizer X versus Y, fertilizer X versus Z, fertilizer Y versus Z, where there is a significant difference. If you want that information, then you have to apply that Tukey HSD test. Okay? So far clear? Application of ANOVA, it's an extension of t-test. Extension of t-test, what we are trying to prove? Whether there is a difference in mean or no difference in mean. Okay. Now if we are trying to test whether there is a difference in mean and there is no difference in mean, then why the test is named as ANOVA? What is the full form of ANOVA? Analysis of variance. And doing analysis of variance, we are trying to prove whether the mean is same or not. Why it is then called analysis of variance? It should be called analysis of mean, right? At the end of the day, what you are trying to prove is whether there is a significant difference in mean of the groups or there is no difference in mean of the groups. Then it should call ANM, analysis of mean. Why analysis of variance? The reason is, pictorially I can try to explain and depict so that you understand, this makes sense. Okay. I can have some data which is distributed like this. So this is one of the data point. And mean of this is coming somewhere here. And I can have another distribution is this. Mean is still coming here. But are these two same? No. Are their variances different? Yes. Right? So I really am trying to prove, and I can have something which is something like this. Mean is again overlapping, but very less variance. So basically, I'm not just trying to prove the mean is same. I'm also trying to check whether there is more scatter in data or less scatter in data. Because to me, this segment versus this segment versus this segment are three different segments, right? But if I just see the mean statistics, they're all same. That's why mean is not the only thing that you are trying to observe. You are trying to see mean with the standard deviation. Whenever you do this and dash, you should always recollect that bullet shot example. 4 bullets, but the center is, average of that is at center. Mean, we got the target. But standard deviation, we did not get the target. Okay? That's why it is analysis of variance. Right? So with that understanding, let us try to understand what is ANOVA test. ANOVA test is calculated based upon the F-test statistics. What is F-test? F-test is basically explained variance divided by unexplained variance. Assume this is the data, which you would have learned in K-nearest neighbor also. Assume this is the data. If this entire data I use and compute the variance of this data, will it be high? Yes, it will be some number, variance will be high. But now if I convert this data into 2 groups, I separate it like this. This is my group 1. This is group 2. Is the variance of group 1 plus variance of group 2, will it be less than the variance, total variance that I had initially? Yes, it would be less. But by grouping them into group 1 and group 2, is my variance become 0?
No.
So the amount which I have been able to reduce the variance, that is what I have been able to explain by grouping them. That is what I have been able to explain by grouping them. However, within this group, there is still a variance. And within this group, there is still variance. That variance still I have not been able to explain. That is unexplained variance. So, explained variance is the variability which is between the groups. The variability which still exists between the groups is the explained variance component. What is the reduction by grouping them, and the variability which exists within this group The variability which exists within this group is what I am not able to explain so far. That is the unexplained part. Unexplained part is the variability which is within the group and the variability which you have been able to express, understand by grouping them apart. That is the between group variability. Okay. So that is the two element. F test is a ratio of between group variability divided by within group variability. Okay. If the value of F is higher, which means the segments are different. Between group there is a high variability. If the F value is higher, which means the segments are different, which means there is a significant difference between the mean. Okay, that's what it is trying to prove as part of F test. Okay, that's what we are trying to prove as part of our ANOVA.
At one point of time, only two groups will be considered. Right?
No.
It can be multiple groups also.
For simplicity, I explained two. To simplify the explanation, I took two. But ANOVA is when it is used?
More than. But at one point, doesn't you can take
In the entire calculation formula, let's see the formula. What is the formula saying? N y I bar minus y bar the whole square divided by k minus 1. This is the between group variability. What is y I bar? Y I bar denotes the sample mean of the ith group. Okay, what it means is there will be a mean of this group. Let me represent by x. There is a mean of this. Let me represent by black x. Y I bar minus y bar. What is y bar? Y bar denotes the overall mean. Okay, which let me represent by, there is no other color, so let me represent by 2x, which is the overall. Okay, so what you are now doing is y I bar minus y bar. You are taking this distance. This is group 1 and you are taking this distance. This is the between group variability, y I bar minus y bar the whole squared. Are you getting? There is the between group variability. N is basically number of observation in that group, because when you are doing y minus y bar, you have to give weightage to number of observations in that group, right? So that's why n divided by k minus 1, where k is number of groups. K is number of groups. Is the first element clear? Unexplained variable. Yij minus yi bar. What is yi bar? Yij is this. Sorry, Yij are these data points. Okay, and yi bar is this. Now this part, there is a variable that is within group variability. This is a within group variability. This you compute. You separately compute this, and what it is saying, summation. You sum up all of this within groups. That is the unexplained component. Divided by n minus k. N is number of observations, total number of observations. K is number of groups. K is number of groups. K here is number of groups. So here degree of freedom is, if there are 5 groups, degree of freedom will be 4. Why 4? Let's understand that. I know the population mean. I know what is the population mean. This is the point where my population mean is. Okay. I know the position of group 1. Let's have one more group here. Let's have one more group here. This is the mean. Okay. I know the mean of group 1. Mean known. 2 mean known. Third mean known. Do I really need to know the fourth mean? If I have this information, do I really need to know the fourth mean? Not required, no? That's why the degree of freedom for that is k minus 1 here. Okay. And that's why for variance, what we do, x minus x bar the whole square divided by n minus 1. Okay. N minus 1 is what we do. That's why we take here k minus 1, because here we are doing the calculation with respect to the 5 or 4 centers. Okay, that's a formula. And at bottom here it is taken n minus k, because the mean of the first are already accounted in the above calculation. Now at the below calculation you take n minus k, because for each group you have to do n minus 1, n minus 1, n minus 1, right? So that's why you have to do, there are 4 groups, so n minus 1 for the first group, n minus 1 for the second group, so minus k is what you take. So this is the formula. Okay. N is the total number of observations. Small n is the particular group observation size. Capital N is the total number of observation. N is the number of observation in the ith group. I have not documented here k, n, capital N. Capital N is the total number of observation. K is the number of groups. K is the number of groups. Source Wikipedia. Okay. Source is Wikipedia. I did not properly snip the image. Yeah. So far clear?
You mentioned for each group you have to do n minus 1 time.
So n minus k is, that's why the formula is, because you are doing summation across all of them. You're in one shot you are doing summation across all of them. Okay. N minus k.
In explain variance, so this whole thing we are doing for all the k groups, right? So I vary from 1 to k.
I vary from 1 to k.
Right?
Yeah.
So, but when you are saying here, you are saying if we have 4 groups and if we know the mean of 3 groups, we no need a 4th, right?
That's why the degree of freedom is.
By calculation, we are considering I equal to 1 to k, right?
Summation wise, you will take no. In the numerator, you have to take all of them. Numerator, you have to take no. Okay, when you do standard deviation, simple standard deviation formula. What is the simple standard deviation? You have 30 observations. What do you do? X minus x bar the whole square, right? In numerator, do you eliminate any observation? No. So here, now assume this data point, this data point, this data point, this data point, only 4 data points is available. And now I ask you to compute the variability. What you will do? X minus x bar the whole square. In the numerator, you will take all 4. Are you going to eliminate anyone? No, that's what I am doing in the numerator, no?
But numerator, why we are saying k minus 1?
What is the formula for standard deviation? N minus x bar the whole square divided by n minus 1.
What's happening?
Right? So we do n minus 1. No? So here k minus 1. Yeah? So far clear? So frankly speaking, all of these calculations, more we go into it, more complexity. But I am trying to detail out as much as possible. Okay, one snapshot, all of that is going to sink in. I understand, no. Conceptual thing, if you understand, if you don't understand this in the first go, I'll say ignore. But if you don't understand this in the first go, I say not ignore. Because you should know when to apply ANOVA. ANOVA is a test of mean and whether mean of the groups are same or not. Why it is called ANOVA, not an ANM? Because you are not just simply testing the mean. If we do simply testing the mean, then I simply go and see the mean value 8, 9, 10, 11, 4 numbers are different. Conclude. But here with the diagrammatic type, I am trying to explain that the mean may be same, but the segments are different. right? So we are really trying to prove are the segments different. We are not just trying to prove are the mean equal. Okay, so so all means are same is the hypothesis. Alternate is at least one of the mean is different. If you understand, and this is application where there are more than two groups. That is the application. Okay, real application is something like this. Real application is something like this. I am trying out something. I am trying out that into multiple parts, and then I am comparing them. The real application is, that is the real application. Okay. Now, for sake of the discussion, I am going to take my hypothesis test data. So here the application is in a banking domain. I want to see whether the balance is maintained by a salaried account holder versus a professional account holder versus a businessman account holder versus a illiterate account holder. Are the balances significantly different? Logically, it should be different. I don't need to do a test also. Logically, it should be different. But I want to prove myself. So I can take the entire bank data segment wise, right? At segment wise, I can take the mean and standard deviation and apply ANOVA. Prove that fact, right? This is banking behavior, that is usage of cash deposit or usage of RTGS payment or usage of internet banking significantly different for salaried, self-employed. I want to validate. Can I validate? I can, right? So some applications. What do we do? First, import the file. We import it. Again, ANOVA makes the assumption, it's an extension of t-test only. So it makes the assumption that samples are normally distributed. That is the first assumption. Second assumption is the data that you are trying to analyze should have equal variance. So this example which I tried to explain, here the variance are unequal, but that was the objective to highlight the concept why variance. So here the second assumption is the data that you are analyzing will have equal variance. So I can have a scenario where I have this distribution, I can have a scenario where I have this distribution, and where I can have a scenario where I have more or less variance may be same, but this may be skewed on one side, this may not be skewed on other side. Okay, because of that mean may still overlap. Okay, so the second assumption is, are the variance equal? ANOVA makes the underlying assumption that the data is normally distributed and variance is more or less equal. Okay, I check the normality using a QQ plot. What did I say? QQ plot should give a line at a 45-degree straight line. Is it giving a 45-degree line? No, which means the balance variable for which I have made a plot, this is a balance variable from hypothesis test for which I have made a plot, is not normally distributed. Can I apply ANOVA? No, I cannot apply ANOVA. But for the training purpose, I am going to apply ANOVA. I don't have any other data, right? I need not, for each example, I need not create a theoretically correct data and then say I apply ANOVA. Jaruri nahi hai na? So I am going to apply ANOVA irrespective of whether the data is not normal. How do I test equal variance? We saw earlier a test of equal homogeneity of variance was Levine test. Now there is another test which I am giving here, Bartlett test. Okay, I can use a Bartlett test. Okay, so here Bartlett test null hypothesis is they are homogeneous, alternate hypothesis is not homogeneous. I see the p value, it is very small, e -21 scientific format, which means alternate hypothesis has to be accepted and alternate hypothesis is not homogeneous, which means again the variance criteria is failing. I can again not apply the ANOVA test, because two important tests that we have to apply on ANOVA is, one is variance should be equal and all variables should be, or the variable, the parameter that you are measuring should be normally distributed. Both of them are failing. But as I said, for training, I am again going to apply this, right? Visually inferencing data, I made a box plot. Again, from visual inference, it is very clear that there is an unequal variance. I need not even have to go to a Bartlett test. From visual inferencing also, you see there is more scatter, more scatter, more scatter. Again, there is the outlier. So typically what you should do is outlier treatment. When there are lots of outlier, typically what you should do is outlier treatment, because outlier is going to impact the mean. So what I am doing is I am doing outlier treatment also. So I am saying, okay, any value which goes above some 4 lakh, because here I see more or less 4 lakh. So any values which are going above 4 lakh, I am bringing it down to 4 lakh. What will have the benefit of that will be, it will reduce the variability. It will reduce the variance. Okay. So I am doing outlier treatment also. Yeah. Having done all of that, I am now applying one-way ANOVA. See, all criteria have failed. All criteria have failed. But despite all criteria failed, I am just for the sake of the training purpose, I am now applying ANOVA. I apply ANOVA, I get p value as, this is print f, this is f test value. The formula is f and one way, that is the one way ANOVA. F is for f test. Okay. So f is coming 1, 2, 3 and p is coming e minus 79. Null hypothesis is coming 0.780 and something. What can we conclude? Null hypothesis reject, alternate hypothesis accept. What is alternate hypothesis? At least one of the mean is significantly different. So we can conclude that mean of the 4 segments of occupation were the 4 groups. The 4 groups in our entire thing is 4 occupation groups. With respect to balance, I am checking whether there is a significant difference in the mean balance maintained by these groups. F test is saying yes, there is a significant difference in the mean balance maintained by these groups. Are you getting? Yeah. I want to know which of the groups are maintaining different balance, because ANOVA is a omnibus test. As such, it is not saying you salaried versus employed, self-employed, whether there is a difference, or whether self-employed versus professional there is a difference. So I have to do a post-hoc test, which is a Tukey HSD test. So Tukey HSD test is saying, what is the outcome here? The syntax is all given up. Okay. Professional is one group, it is comparing the data with a salaried. So here reject null true. Professional self-employed, difference is this much. This is the difference in the mean. Reject null true. This is the difference in the mean between professional and self-employed non-professional. Reject null true. Salaried self-employed, the difference is very small. Reject null false. So basically these two groups are same. Rest of the groups are means are not matching. Okay. So reject null true, true, true. Reject null false, which means true reject null is true, which means accept alternate. So accept alternate means there is a difference in the mean of professional and salaried. There is a difference in mean of professional and self-employed. There is a difference in mean of professional and self-employed non-professional. So that's what the test is. All permutation combination, that is what the method is doing. Tukey HSD test is automatically doing it for you. What now you say sir ने तो सब कुछ तो सिखा दिया और बोल दिया कि ना सब conditions, all conditions are failing. Still sir has went ahead and taught apply ANOVA. if all conditions are failing and you do not want to apply ANOVA because conditions are not meeting, then use Kruskal-Wallis non-parametric test. Okay. It is used in place of ANOVA if the distribution is not normal. My distribution is not normal. So I apply a Kruskal-Wallis test. Okay. See, I am not going into syntaxes. Please understand. I am not explaining line by line syntaxes. Okay. Or to call a Kruskal-Wallis, you will have a Kruskal function. Okay. I am not doing that. We have got
the interpretation. Before we go here, what is the difference between ANOVA test and 2K HSD test, the one which
2K HSD test is, see, ANOVA is an omnibus test. It is not telling you which groups are different. But if I want the detailing also which groups are different, I have to go to a post-hoc test, and that post-hoc test is 2K HSD.
So this part I got it. So like, I mean, directly cannot we go for this post-hoc test without going through ANOVA?
Go.
We can.
Nothing stopping, because the syntax of that is not making not taking the output of ANOVA as input to that. You can go.
So I mean, this would be more effective if we do that, is it?
No. Most of the time you will use ANOVA test only, because most of the time when your statistics is thrown out, you will get ANOVA output only.
But why do we do that? Because this looks to me more convincing.
This is just an extension where probably I would have said you really want difference between group 1 and group 2. Why go with ANOVA? Why go with 2Q HSD? Take that 2 group and apply t-test. No? See, t-test is what it is doing. It is giving you a difference between 2 groups. No? Group 1, group 2. Apply, create a pair of 2 groups, run t-test, apply, create a pair of 2 groups, apply t-test, apply, create a group of 2 groups, apply t-test. ANOVA is more used for many other analysis also. Okay. For example, when I do a linear regression also, you will get an ANOVA outcome. When you are getting a linear regression between 2 variables, which are x and y, both continuous. In x and y, when both of them are continuous and you have built a linear equation, in that case, you still have the explained variance and unexplained variance computed in linear equation also. So you can apply a ANOVA test. Now, in that case, you do not have explicitly the groups. Please understand, there is a x which is a continuous variable, there is a y which is a continuous variable. I am fitting a linear regression between x and y. When I build a linear equation, I get the predicted value. That predicted value is trying to explain the y. So I have got the explained variance, and what the predicted value is not able to explain, because there is still a gap between predicted value and the actual value. That is the unexplained part. So still I have got explained variance and unexplained variance. Now in that case, do you have groups like professional, salaried, self-employed, SENP and all of those things? You will not have groups. Now how are you going to apply QQHSD? We can't. That's why I am saying ANOVA has got more applicability. This is in a specific case where you want that difference between 2 categorical variables. In that case, you can do an extension of ANOVA and get this outcome. But in the earlier case, you cannot apply, no? So ANOVA is more applicable, more generic. Okay. Only limitation, it is not explaining. Now in that case, in linear regression, I really don't have groups, so I don't really want that outcome coming, this detailing of TQ. But here specifically, when there is a specific requirement, TQ will be helpful, right? So I applied the ANOVA test despite all conditions failing. So you say, sir, kuch to sikha ke chale gaye. It did not teach us when to apply when all conditions are failing. In that case, it's a Kruskal-Wallis test. Okay. So let me just go through the commentary of this comment statement. I already explained that whenever you make a parametric test into non-parametric test, it typically converts data into ranks. So what is the definition? Rank all data for all groups together. which means I will not going to see the groups. I'll see the balances, put them in a ascending or a descending order, and then say lowest balance is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, highest balance. I'll keep giving incremental numbers. Irrespective of the groups, first I will just sort the data by balance and give numbers. Okay. Now, if there are more lower numbers coming in group 1 and more higher numbers coming in group 4, obviously there is a significant difference in the mean, right? This is what the Kruskal-Wallis test is doing. This is what the Kruskal-Wallis test is doing. Rank all data from all groups together, that is rank the data from 1 to n ignoring the group membership. Assign the tied values, the average of ranks. If there is a particular value coming 10 times, I cannot then say 10, 11, 12, 13, 14. Then for all of those same repeating value, I have to give them same group number. So that is what is a typical ranking approach. For example, in a class there are 5 students getting 100 out of 100. Can you say now the name which starts with A is number 1, class number position 1, and the name which starts with Z will be class position 5? No, you do not do that partiality, right? So here what it is saying, if there are values which are same, then you give the same position number. This is what it is doing. Having done that, now based upon the mean value of the rank, I just see the mean of the group 1. What is the mean of all the ranks coming? What is the mean of all the groups 2 coming? What is the mean of group 3? What is the mean of group 4? If the means are significantly different, which means the groups are different. That's how a parametric test is converted to a non-parametric. Are you getting? So here I am not using actual mean and standard deviation. Now I am using ranked data. Benefit of this is, again, you don't have to do any outlier treatment. Now if the outlier one value is in the balance 1 crore, anyways, if I have got 20,000 observation, 19,000 value is 5 lakh and 20,000 value is 1 crore, the rank will come 20,000 only. It's not going to become 20 crores, right? So it also eliminates the outlier problem. So if I apply this, the interpretation is,
when you say a significant difference between the two,
if P is greater than alpha, fail to reject H naught. If P is less than alpha, reject H naught. So here my P value is coming too small, which means I reject null, accept alternate. Conclusion is there is significant difference in the mean. Okay? Yes, sir. So you are asking something.
so when you rank between different groups, right? So when you try to find the difference, so you find the review first group, second group, and first group, third group, so all kind of combination.
No, again it will do across all of them together. It's not going to say which group is compared to other group. Say output is not saying which group is with respect to other group, no? Outgroup is across groups. So it is also not going to say which group is compared to other group. It's like also omnibus. Yeah.
Is internally using mode actually?
Sorry?
Is internally using mode?
Mode is
Frequency, right? You're saying?
No.
Nothing to do with
That has nothing to do with mode. Nothing to do with mode.
You just sort the data.
Sort the data.
Index number from
Yeah.
sequentially.
And same
And
value
see,
you only put in.
then go to the category. I mean, if practically you wanted to go to the category, then check which category have less index number and more index number. Like one which have 3, 4 like that. And some category will have 10, 20, 30. Then find the mean and see if there is any difference. Then
So you find the mean of what?
Rank.
index.
Ranks.
That
Ranks.
For each rank, you have to find the mean.
For each group, using the rank values, you compute the mean. And then if there is a significant difference in the mean of the ranked values, there is a difference in the group, which is a very logical thing, right? That's how what they are doing is converting a non-parametric test to converting a parametric test to a non-parametric. That's the approach. And most of the time you will see many of the tests where you see non-parametric test is there, which we cannot apply because of test of normality, equality of variance. Then you convert it to a non-parametric test. Many of the time it will be converting the data into ranks. Okay. So the test that we have seen is Z-test, T-test, ANOVA. All of these are parametric tests because they are completely dependent on mean and standard deviation for their calculation. One test which we have seen in non-parametric is a Kruskal values test. Okay.
So you can only use one measure at a time, is it?
One measure at a time.
No, in this case it's balance. So what?
Yeah, obviously. Across group, you're going to see one measure only. When you're testing, one hypothesis only one test. No, hypothesis will, you cannot have a hypothesis. There is a significant difference in mean of the people and age of the people in professional group. There are two tests you cannot do in one go, and that's where design of experiments, multi-way ANOVA. If you have more than these parameters, output will be still one, but more than one dimension you are testing. Okay, and across two, there is a two-way ANOVA, multi-way ANOVA, right? So I have not executed the code, but the code is given in the IPython notebook statistics.ipynb file. Kindly execute the codes.
Another test like earlier we got like numbers per percentage. So here we
don't get confidence. No, we always get alpha. Significance. Alpha, 1 minus alpha is so confidence. 1 minus alpha is the confidence. Simple. 1 minus alpha is the confidence. Okay.
We have F table as well, like the Z table, and
yes, you have F table.
from which we can get the P value.
Yes, from that you can get the P value. So when you have to see F table with P value, you will have 2 degrees of freedom that would be given all of those information, because there is a group variability degree of freedom, that is explained variance degree of freedom is there, and there is an unexplained variance degree of freedom, and there is a F value. So you have to see combination and then take the value, but we will not go into that. We will use the.
So in the code, because we have converted the outliers, right? 4 lakh values to.
Yeah.
When we are applying one.
I have not used that. Use that outlier, apply that. In code, if I have not applied, change the column name. Change the column name and take the treated column. It will not make significant difference. Because when the outcome is coming e to power minus 7980, I'm not going to change. If the outcome would have been e minus 1 or minus 2, then I would have expected significant change in the outcome. This is ANOVA, this is okay, right? This much you are able to run? Then which one? This one QQ plot you are able to run? This Bartlett you are able to run? You are able to run? Then this box plot you are able to run? Then this capping code you are able to run? And what sir has said that I've done capping, but I have not used the cap column in the calculation. You can use the bell cap column, not an issue. Okay, you are able to run F1 way, import that and run F1 way. Okay, don't go in this OLS. Okay, OLS is ordinary least square, and if you run a regression, a linear regression. Okay, if you do a linear regression, you will see you will get the same output. When you run a linear regression and get a ANOVA test output, you will get the same thing, same output as you run using ANOVA function. This is just what I am trying to show here, that I am fitting a ordinary least square, that is a linear regression between balance with respect to occupation. Once I fit a linear regression and then I see on the linear regression what is the F value coming. This value which you got 123 here, the F value, the same value 123 you are getting. So when you run a linear regression and simple linear or multiple linear, you will see one of the outcome of the linear regression is the F test outcome. Okay, and that's what I was trying to explain, that why can't we directly apply QQHSD? Why we need to go to ANOVA? Okay, ANOVA can be used if this variable, instead of putting this variable, if instead of taking occupation, if I would have taken a variable, say number of credit transaction values are 0, 1, 2, 3, 5, 6, 7, 8, 9, 10, 100, 200 like this. In that case there are many groups, right? But still if I run this code by changing that column from occupation to number of credit transactions, you may try, and then I get this outcome, still I will have the F value coming. Okay, because when I run a linear regression, I predict the values. The difference between the predicted value and the actual value is the error which I am still not able to explain. Okay, so that will become my unexplained error, and summation of unexplained error squares divided by n minus 1 observation, that will be unexplained variance. The difference between the mean of the overall data minus the predicted value is the explained variance. Okay, so I can compute explained variance and unexplained variance in linear regression also. Okay, and in that case I can compute ANOVA, because ANOVA is what? A ratio of the explained variance divided by unexplained variance. So I can do ANOVA there also, no? So from that standpoint, QQHST will not be applicable there. Okay. नहीं देखो, अब मैं फील के लिए एक कंक्लूडिंग स्लाइड पे हम जाएंगे. सबका कोड रन करके हो गया. ये काई स्क्वायर टेस्ट अभी करना है, बट बिफोर आई रन काई स्क्वायर टेस्ट, आई टू माय माइंड I realized that yesterday I said I'll do sampling calculation and I missed this 2 slides. तो एक बार काई स्क्वायर के पहले सैंपल का भी खत्म कर ले, sampling calculation, otherwise this will remain pending. Now the question that one of the question that we had was, how do I decide my sample size? Right, I'm taking I took an example 1 lakh population, and from that 10,000 is sufficient, not sufficient. Okay, then you said, okay, whether it's sufficient, not sufficient, we don't know, and that's why many of you said no, it may not be representative of the population. But how you typically decide the sample size? So I'm going to take that same SAMI example what I have in my PPT to explain that concept. There's a population, there's a sample, there's a parameter estimate. Mu, this is a population parameter estimate, and I compute for the sample the mean, that is x bar. This x bar I know will not be equal to mu, will not be 100% equal to mu. If I take one sample sufficiently large, still despite taking sufficiently large, this x bar will not going to be equal to mu, because there will always be a sampling error. Now the question is, how much of the sampling error you want to tolerate? Okay, sampling error means what? More standard deviation of the sampling distribution, right? So how do I narrow down the sampling error? To narrow down the sampling error, which means I want to narrow down the standard error. Standard error, if I reduce, my sampling error will reduce. What is standard error? Standard error is standard deviation of the sampling distribution. That is standard error. And what is the formula of standard error? Equal to sigma square divided by, if I take in terms of standard deviation, standard error, if I'm meaning standard deviation, not the variance, in that case it will be sigma divided by root n, right? That's what we understood. So here in this example, in the SAMI's example, we had x bar as 30,000 and sigma as 8,000, n as 400. So standard error in that case was 8,000 plus or minus root of 400, that is what is coming as 2,400, right? What does that mean? for this sample the mean came as 30,000. The true mean at a 95% confidence, what would be the range in which the true mean would exist? The range at a 95% confidence, the true mean will range in range of true mean, and I want at a 95% confidence, which means the range of the true mean will be x bar plus or minus 2 sigma. So x bar minus 2 sigma would be 30,000 minus 800. So this will come out to be 29,200. On the higher side, it would be 30,800. So this would be my range.
Because sigma is 800 or 8,000?
8,000.
Because it is 8,000.
Here, it would be the sampling distribution error, no? Here, it will be standard error that would be coming now. Because the mean is of the, this is, we have to take the, of the sampling distribution.
Actually, they are confused. You have written sigma as 800.
So that's a standard
No, here still
No,
it's
there
8,000.
by mistake I have written 800. It will
That
be
should be
8,000. Yeah.
It's okay.
Okay.
That is overall standard
So-
deviation by 8,000.
That is 8,000. Yeah.
Overall.
So this is the range. So from the sample, where at a 95% confidence, I can say the minimum of that locality would have been, the minimum income of that locality would be 29,200 and maximum would have been 30,800. However, now I am the person who have given this business to you to do the survey. And I say that the range in which I want the final outcome to come should not vary by plus 100 and minus 100. Okay. I say that on one side at a 95% confidence level, the range should be plus 100 or minus 100. So whatever number you come, you do survey, you go to X number of people, you give me the mean of that, and having computed the mean, you should give me a range that the true mean will lie in this. But I am saying whatever mean you quote, plus 100, minus 100 is the range which I want. Okay, at a 95% confidence. So now I know at a 95% confidence, 2 standard error can be equal to 100. So my standard error can be max 50 only. If I know my standard error can be max 50, and what is standard error formula? Sigma divided by root n. But now I know this 50. This is 8,000. Root n is unknown. Root n is unknown. So I go this side, root n is equal to 8,000 divided by 50. So this is 5 1 5. But this is root n. So I want n. The n is the number of observation, right? 16, 16 the 256. I need these many observations in my survey. Are you getting? These many number of observations you will require. Now you will say, okay, sir. Now you will say, sir, okay. You said you want plus or minus 50 range, which means I have to do survey of 25,600. So the billing will go from 400 to 10 times is 4,000, 20 times is 8,000, 25 times. So 60 times the cost increase. Right? So you give me, sir, that much money. We'll do that much survey. Are you getting? No, you will go, no. I cannot pay 60 times for this kind of a thing. right? Okay, you give me plus or minus 200. Okay, plus or minus 200. I do again the calculation. How many people? Survey. Right. So that's how the sample size is computed. Are you getting? So whatever is the main parameter estimate, with respect to that, you say, okay, this is the confidence limit in which I want the range, the actual value to play around. You do the reverse computation, you get the sample size. Yeah.
Just one question.
Yeah.
When coming to ML and sample size, we do trend test split. There also this same rule will be applicable.
See, train test split. Thumb rules are 50 and 70-30. Okay, and typically you will have observations which is 1 lakh. To analyze 1 lakh, you already have data. To analyze 1 lakh, not a creating 70-30 here. You don't have to go out in market and do survey and all of those things. So you got 1 lakh. But the question, real question is not with 1 lakh. Real question is I've got 1 crore observations. Now with 1 crore observations, should I build model going with the 70-30 rule? Then it will be 70 lakh as modeling, development based, training based, 30 lakh will be testing based. The question is relevant there. Not with the 1 lakh and 2 lakh observation, or not with 100 observation or 1000 observations of a breast cancer example you would have done. Right? That's where the question is.
If that kind of scenario will come, then we have to do this and figure out what is the confidence.
And the model should be built.
If you do Google search, you say sample size calculator. It will ask you what is the n, what is the confidence interval, and what is the value that you are trying. Okay, what is the range? All of those it will ask, and then you get the sample size. All those calculators are available. You do on the always you will do on sample only, right? So those things are all available. These are all outcomes of these kind of things. Yeah. So I would completed the sample size. I don't think so I skipped any slide in between. ANOVA we have done. Chi-square. So all the tests that we have done so far are parametric. So now one important non-parametric test is chi-square. Chi-square is a non-parametric test. You will see in the calculation, it nowhere depends on mean, it nowhere depends on standard deviation, it depends upon the frequency of observations. This example which I had discussed earlier. 2000 people in a locality were exposed to smallpox. 500 in all were attacked. Of the 2000, 600 had been vaccinated, and of which only 50 were attacked. And this is the data. This I discussed when we discussed association of attributes. I said Yule's coefficient of association can be used, but then I said we will not go in detail of Yule's coefficient because it restricts only when A, B, A, B. 2 by 2 matrix is there. But when you have a data which is like this, where you have got many categories, Yule's coefficient of association will fail. Okay, so that's why I said, okay, let's go with something which will be applicable in 2 by 2 scenario also, and n by 2, n by 3, m by n scenario also. So that is chi-square. So chi-square is a test of association. There are 2 applications of chi-square. One is chi-square as a test of association, and second is chi-square as a test of goodness of fit. Okay. So first let's see test of association. How we are going to compute chi-square. This slide is trying to explain m by n structure is given to you. These are different y categories, these are different x categories. Okay. So you will have actual frequencies of those intersections. Once you have actual intersection, actual values, you have to compute something called expected. You have to create the similar grid, and these intersection cells, you have to populate what is the expected values. Having computed the expected values, you take observed, which is the actual value minus expected value, the whole squared, divided by expected. You do summation of all of that, and that value is called chi-square. and then using that chi-square distribution table. Again, when you see chi-square distribution table, you have to see it with respect to degree of freedom. So degree of freedom of this would be, if there are say m categories here, m minus 1, and if there are n categories here, n minus 1, the degree of freedom of this cross tab would be m minus 1 multiplied by n minus 1. That would be the degree of freedom. So basically you will have two outcomes coming from here. One is the chi-squared value. Second is the degree of freedom. You take these two, go to the chi-square distribution table, see the p-value. Okay. So what is the null hypothesis in chi-square test? Because once you get the p-value, you have to validate against the null hypothesis and prove whether null is true or alternate. So null hypothesis is observed frequency is same as expected frequency. Observed frequency is same as expected frequency, which means the values that you have in actual, and once you do some expected calculation, the expected calculations and the actual values will be same. And if the observed frequencies are same as expected frequency, the interpretation of that is x does not impact y. That is, there is no association between x and y. Okay. So status quo, before you do the test, status quo is we do not know the association. So for us there is no association. That's why we are not being using it from a model point of view. That is status quo. The reason why we are testing it, because we feel that hey, x impacts y. So that's why you are wanting to see whether there is association. Okay. And to prove that, that is the alternate. Chi-square test can only be applied when the variables are categorical. If you have a continuous variable x and continuous variable y, you cannot apply chi-square test. In that case, you have to run a regression between continuous variables, and the regression test is going to make use of a z test or a t test to say whether the outcome is significant, that is x impacts y or not. Okay. For now, we are in a parametric, non-parametric test, chi-square test, applicable only on categorical variables. Is that clear? Now the question is, I have explained the null and hypothetical. There is no relation between the two nominal, that is categorical variable, or there is no significant difference between the observed and expected, which is what I explained. Alternate is there is relation between the two categorical variables, which means there is a significant difference between the observed value and the expected value which I am going to compute from the observed table. There will be a significant difference, and it is a non-parametric test. How are we going to run the chi-square test? I'll sit, I'm also tired. So here we are trying to see relation between vaccination and smallpox disease. This is vaccinated set of people, these are not vaccinated set of people. These are the people who got the smallpox disease, these are the people who did not get the smallpox disease. The numbers are actual numbers, observed numbers. So what it is saying, there were 600 people who were vaccinated, of which 500 got smallpox, 550 did not. There were 1400 people who were not vaccinated, 450 got smallpox and 950 did not get. And if you recollect last time when I did Yule's coefficient, when I was explaining, I showed the same slide. What you people did is you quickly computed the frequency proportion. You said 50 out of 600 is approximately 9% people who got smallpox in a vaccinated segment, and 450 out of 1400 or approximately 30 people got smallpox out of non-vaccinated segment. 9 versus 30, there is a significant difference in the proportions. That's why vaccination is effective. Very logical conclusion we quickly reached. Only thing is now we have to reach that conclusion statistically. I have to now compute the expected matrix. How would the expected matrix look if there was no difference between smallpox occurrence in a vaccinated segment versus non-vaccinated segment? So how do I compute the difference? To compute the difference, I first see the grand total. Total, how many people are there? 2000. Out of 2000, how many people got smallpox? 500. How many did not get smallpox? 1500. So in a overall population, 25% were attacked by smallpox, 75 were not attacked. Are you getting overall what is the scenario? If there was no impact of vaccination in preventing the smallpox disease, in that case, in the vaccinated segment, I should have 25% people getting smallpox, right or wrong? And 75 not getting smallpox. Likewise, in a non-vaccinated segment, I should have 25% people getting smallpox and 75% not smallpox. The proportion should not be 9:30. In one side it was 9, other 30. It should be more or less same. Right? That's the logic. Right or wrong? With that logic, we now compute the expected table, because overall proportion is 25:75. We now say out of the 600, according to equality of proportion principle, this should have been 150, this should have been 450, this number should be 350, and this number should be 1050. That's how my calculation should look like, right? Now my chi-square formula. What is the chi-square formula? Observed minus expected the whole square. These four numbers, 50, 450, 550, 950 are observed numbers. This 150, 450, 350, 1050, these are my expected number. The formula is observed minus expected the whole square divided by expected. So 50 minus 150 the whole squared divided by 150 plus 550 minus 450 the whole square divided by 450 plus 450 minus 350 the whole square divided by 350 plus 950 minus 1050 the whole square divided by 1050. So this is the summation of observed minus expected the whole square. If I do this entire summation, I have done this. 50 minus 150 the whole square divided by expected 66.67. 550 minus 450 divided by the whole square divided by 450 is 22.22. I have done this calculation and done the summation. It comes out to be 127. Okay. Degree of freedom m minus 1 multiply n minus 1. So how many categories are here? 2. Column wise how many are there? 2. 2 minus 1. And how many categories are here? Row wise? 2. 2 minus 1. So 2 minus 1 multiply 2 minus 1. That is 1 multiply 1. That is 1. So degree of freedom will be 1. I have to now see the p-value. Now without even going into the p-value, can you tell me logically, if chi-squared value is higher, this observed minus expected the whole square divided by expected, this summation is higher. If high chi-square value is there, does it mean there is a significant difference between observed frequency and expected frequency? Yes. Because if observed minus expected is significantly different, then only the square will be significantly different. Right or wrong? So when the number is very high, in that case, observed minus expected, this will be higher. Higher chi-squared value means there is a significant difference in observed and expected frequencies. So without going to p-value also, logically by seeing that, I can to some extent conclude that there may be difference. But really it will be concluded based on p-value only, because you have to see this fact with respect to degree of freedom. So I see the chi-square value with degree of freedom and I get the p-value. This is the p-value. So what is the p-value here? E minus 29, which means 0.28 zeros and then 1. Now interpret with respect to our hypothesis testing interpretation. So what will be the conclusion? Alternate hypothesis has to be accepted. First, immediately we have to conclude that alternate is accepted. Now definition of null and alternate in case of chi-square. Null in chi-square is both are same, observed and expected are same, which means there is no association between vaccination and smallpox disease. Alternate is observed and expected frequencies are different, which means there is an association between vaccination and smallpox. And alternate hypothesis is validated, and by physically seeing the numbers, we see that inoculation is reducing the occurrence of the disease. Because for example, if this number 50 would not be placed here, it would be 550 and this is 50, still my number would have come like this only. Right? In that case, the conclusion would be inoculation leads to more smallpox. Right? Here the test is only saying you whether there is an association or not. But whether it is a positive association or negative association, the test is not saying you. I hope you are getting the point. Yes, no? Right? So physically, while finally making the conclusion that inoculation is effective, you have to see the proportions and then make the conclusion statement. Yes, sir.
I was just asking, how did we calculate the p-value? I read the last line.
Okay, p-value, yeah. In Excel, this is the formula. Okay. Can someone give me the statistical book? I did not explain the f-test, but I said you that when you interpret f-test, it's slightly complicated, because if you see f-test, there is a degree of freedom here, there is a degree of freedom here. Both the sides there are degree of freedom. Why? Because there is a numerator degree of freedom that was k minus 1 and there was a denominator degree of freedom n minus k. So when you are seeing f-test, you have the f value, you have degree of freedom, 2 degree of freedom. That's how you go through it, and it's not that easy. That's why I did not want it to complicate. It's taking 5-6 pages. Okay. That's why it's better to do Python. But let me just explain the chi-squared one. This is a T. I'm just trying to find. This is page number 544. Critical values of 544. Critical values of chi-square. Chi-square is represented by x square something. X is like that Greek kind of a symbol in which you write that. It's not proper x. Okay. So here, if you see, the alpha is given here. This alpha, basically you have to read the number, whatever number is going to come, the alpha is going to come here. If you specifically see the Excel, it says chi-square.dish.rt. chi-square.dish.rt. RT is right tail. Why specifically when we are doing a chi-square, we have to see the right tail number? Let's try. Yeah, sir. It's not because of square. Chi-square is not a normal distribution, first point. Okay? Chi-square is not a normal distribution. It's a non-parametric test. Right? Now, the way on the x-axis is the chi-square. On the x-axis, you have the chi-square value. This would be one chi-square distribution graph, say it is for degree of freedom 1. Then you will have another distribution graph which will be for degree of freedom 2. Then you will have another graph which will be for degree of freedom 3, degree of freedom 4, degree of freedom 5. How that chi-square created all of those, we don't have to go. But they created all, that is huge thing. Okay. So first you have this distribution graph you have to see with respect to a degree of freedom. Now logically think, if observed frequency and expected frequency are not matching, will the chi-square value be higher or will the chi-square value be lower? It will be higher. Now as my chi-square value go higher, let's assume we bother about the black graph because that is for degree of freedom 1. As the difference in the observed and expected is becoming higher and higher, what it means is null hypothesis should be more, we should become more confident in rejecting it and accepting the alternate. This value, this line, as chi-square value go higher, this line will keep moving up. In that case, whether you want the smaller part or the higher part to be the p-value. P-value is always for the null hypothesis. P-value is always for the null hypothesis. As the value goes higher, that is, there is a more difference in observed and expected frequency, only then the chi-square will be higher, right? In that case, you want the p-value to come higher or lower? Lower. That's why logically you have to take the right hand part of the tail, right? Not the left hand side. Because as the value goes higher, the left hand part will keep increasing. If the value p-value comes higher, you will say null hypothesis accepted. But on the contrary, what we have to accept is the alternate. That's why it's a RT, right tail. So you have to see the right tail element. That's why in Excel the function is given chi-square.dish.rt clearly. Okay. So this is this problem I have solved in Python. How to solve in Python? I'll explain. But for that, let's take another example. Here, this one is computed in Excel. Entire thing is done in Excel, and the function in Excel is this. But conceptually, calculation understood? Yeah. So let's take another example. You have done a survey of 400 households on education level. 400 households you do the survey and see who is the highest educated member of the family. Based on education level and the place they stay, so education level you have classified 4 categories: graduation, post-graduation, professional, illiterate, something. So you have got 4 categories which I have given. And based on the flat, apartment, chawl, wherever they are saying, you have made them 3 buckets. The socio-economic status is above, middle, below. Based on education and socio-economic status, you have to now draw a conclusion. Does education level influence the socio-economic status of the household? The data is given here. Okay. And again, these kind of social projects also you can take as a capstone, where you say that I want to do association analysis about this factor impacting this factor or not. You can take that as a project, right? For example, you can take hygiene. Hygiene impacts health. Okay, you can take that project. Then you can see various areas, localities. What is the hygiene levels of various localities? You can classify, you can create some subjective groups. Okay. And based on that subjective groups and based on some survey, you can get how many people are in that area getting ill, hospitalized or something, right? At a 0.05 level of significance, is there evidence of relation between socio-economic status and education level is the question. So the observed frequency is given. Expected frequency, you copy paste the numbers in Excel and create the expected frequency and chi-square. Only when you do, you will understand the calculation. So compute the expected frequencies and compute the chi-square value. How to do in Python is there. If those who are bothered of the code, Python code is there. NP chi-square contingency. I have to put this in a contingency format. I compute from the formula. I compute the chi-square. I compute the p. I compute the degree of freedom. I compute the expected frequency matrix. I get all of those output. Okay. How to do in Python? Given, right? For calculations, you see this, compute the expected table. outcome of expected table is here. This is the outcome you should be getting as an expected table. Then observed minus expected the whole square summation you do. This is the value you should get for the chi-square. This is the value you will get for degree of freedom, and this is the p-value. So all of this is given in the next slide, but try to do it in Excel. Python is 4 lines copy paste code, which you don't even have to do. It's given in IPython notebook.
If the values are coming in decimal, because in this case,
Obviously,
percentage, so we'll take the decimal.
those who are not able to compute or taking time, I'm doing the calculation here. First is what we have to find is the the overall proportion. How is the overall 400 data distributed? Okay, so 164 divided by 400 F4 enter. So I know the distribution is like this. What it means, I have to create the expected table, which means above, middle, below, for the category wise, education level wise, the distribution should be 80 into 0.41. Okay, so let me put F4. F4, if I move right, I want C becoming D and D becoming E. So I'll require that thing. So, right. So I did that, sir. So this is how Excel becomes fast. Okay, so done. You need to just cross check whether the calculation is right. In that case, you have to do summation. The summation is coming 44. No, the value should have been 80, which means somewhere I am wrong.
The second
So
one should be
C,
21.4.
21.1.
Middle should be 21.4.
the middle should be 20. So I have to make this also constant, right? So I now need to make F constant. F should become constant. Okay. So sometimes very fast Excel can give you wrong output. But now it is correct. 80, right? This is a cross check. Sometimes what happens when you do these F4 and all those things, we may go wrong. So cross check, my numbers, row totals are matching. 200, row total is matching 40, row total is matching 80. So that is my calculation. So now this is, let me put the header, merge, let me say it is expected. What is chi-square? Again, you have to simply do copy, create a same structure, and then say equal to observed minus expected the whole squared. This time I don't have to do any dollars. F4, so I don't have to run. Control V. Chi-square is equal to summation of these values. Done. Finish. What happened? 67. 67. Done. Finish. There's a chi-square. Degree of freedom. Degree of freedom is equal to 4 minus 1 multiply. दोनों करना है ना सर, दोनों करना पड़ेगा. 4 कैटेगरीज है ना एजुकेशन में, so 4 minus 1 multiply 3 minus 1. That is the degree of freedom. Okay, then p value, the function which I showed was chi-square dot dish dot rt, right? So chi-square dot dish dot rt is what we have to take. It says x is this, the chi-square value. It says degree of freedom, we have to give this. This is my degree of freedom, 1.55. The other way of doing chi-square would have been equal to chi-square dot distribution, chi-square test, and then it says actual range. I take this, comma, observed range, I take this. I just do bracket close, I get the degree of p value. Yes, sir.
The formula I mentioned x square is equal to
Chi-square, not x square, chi-square.
no, in the slide presentation it mentioned x square. In the formula Excel it shows that x comma freedom.
Where this one?
Here.
This one, right? I said that chi is represented by symbol x. Slightly variant of chi x is what? It is not x square, it is chi square.
my question is like that chi-square in Excel, it is shows x comma degrees of freedom. Should we do square root of that?
That is chi-square. X is a parameter name. Can you give a parameter name in Excel which is x square as a parameter name? No. That is, sir, like this, equal to, let's go here, this one, equal to fx. Let's run this. What it says, x. X is the value at which you want to evaluate the distribution, a non-negative number. And here, because we are using a chi-square function, we have to understand that x parameter is chi-squared, right? So done. And the same thing, how you can do in Python, I have made this as a NP array, right? So first 3 elements I have put in one, second 3 elements, third 3 elements, then fourth 3 elements. I have created a 2-dimension array, right? Having created the 2-dimension array, I have called chi-square contingency function, chi2 contingency function, and passed my obs, and it displays me the outcome. So 67.17, let me cross check with my Excel, 67.17, degree of freedom 6, degree of freedom 6, p value 1.55, p value 1.55, e minus 12, and this is the expected array 32.8, 21.4, 25.8, where is this 32, 21, 25, 82, 83, 82, 53, 64, and this entire matrix is matching. Done. Chi-square done. So chi-square is a non-parametric test used to see association. That is one application. This is another. I don't have to create array. I don't wish to create array. The data is already in my data frame. Okay. If data is already in my data frame, I am taking 2 columns, categorical column, occupation versus target. Okay. So I can do a cross-tab function. It creates this n-dimension array structure. That cross-tab function, I use that in chi-square contingency. Finish. I get the outcome. You need not type, right? Someone will say, sir taught us how to type and create a series, but my data is actually in rows and column in data frame. So how do you do? 2 columns you want to do, automatically the frequency cross-tab is done, and you run the contingency function, you automatically get the outcome. Done. Chi-square, I said 2 applications. One is goodness of fit and second is association of attribute. What we saw was association of attribute. Now I am going to explain goodness of fit. This goodness of fit is now going to clash with your KNN what you learned. In KNN what you learned was you want to prove the alternate is true, right? You want the variable to be significant. That's what you learned, right? You wanted to, because the reason why you wanted to do is the model variable is significant is what you are trying to prove. Now, if the problem statement I have is I have created the model. Now my problem statement is the model fitting the actual? Now my objective is not to verify whether the individual variable in the model is significant or not. My objective is now is the model overall, the outcome of the model fitting the actual. Okay. So in that case, typically what will happen is you have an actual column that is probably you had the column as target. What was the column name? Target. So diagnosis. So diagnosis was the column name. Let's also call it diagnosis is our target. Okay. And here you had something called malignant, benign, like this, right? Malignant, benign, something. This was the kind of values you would have got. You built a KNN model. KNN predicted class. Okay. And based on that, you said malignant benign, There would be some cases where it is malignant, but you said benign. There would be some cases where it said benign, you said malignant. You would have done that. Can I apply a chi-square test on this? Can I apply a chi-square on these two columns? Yes. Now here, if I apply a chi-square, so I'll have one side, I'll have model output malignant, benign, actual output malignant, benign. This is the actual observations where you have taken actual model output and actual output which is the given. Can you compute the expected outcome? Can you compute expected outcome? Yes, we can compute expected outcome also. So you will create an expected outcome table. Do you want this number and this number to match or not match? Why you want it to match? Because only then, if the expected numbers were very close to what is the model, in case model is right? So in this case, your objective will be null hypothesis to hold or null hypothesis to fail. To hold. So in this case, your objective is to see how good is the model fitting to the data. And that's why the test here is not to see association. The test here is to see goodness of fit. So this is called goodness of fit test, where we can use a chi-square. So here I've just created that a model has given me very high, high, moderate, low, very low risk levels, 5 risk levels, and these are the actual frauds and no frauds. Compared to that, there is a model classified frauds and no fraud. Okay. So if actual and model numbers are matching, my model is a good model. Right or wrong? Actual and the observed, a model predicted numbers. In high risk, the actual numbers were 25 and 500 no fraud. Model predicted in that there will be 22 cases of real fraud and 503 no fraud. These two numbers are very close to each other. So observed minus expected will not be different. So model is able to categorize. Here in very low, it says model was there is actual 3 frauds and 2000 no frauds. Model said here I should only have 1 fraud and 2002 no frauds. Numbers are very close to each other. If I do a chi-square test, it will tell me how good is the model fitting. So that is what a goodness of fit test. Are you getting? So with this was 175th slide. Yeah. So now we just have one more some practical application. So A/B testing. How many of you know what is A/B testing? A/B testing. So you're done A/B testing? Yeah. So how do you finally validate that A/B test is working, not working?
Basically, just trying to run 2 offers at the same time.
Yeah.
You know which offer will perform better.
So how do you finally judge whether A offer is better or B offer is better?
Based on the response rate.
Based on the response rate. So here one side you got 14%, A you got 14%, B you got 15%. Which is better?
50 is better, but you cannot say statistically.
So do you just see 14, 15 and then 15 is more, then you go and say 15 is better?
No, how many the customers operate for that, and finally conversion also you see.
So I assume 14% conversion, 15% conversion. Then, right? Do a t-test or do a z-test. So basically what you will have to do, whether really this is working or not. Okay. Please understand what we are discussing was A/B test. In A/B test, what you do is you take offer A, you offer B, you have say probably you are seeing click rates. You have got 2 ads running on your Google. One ad is one creative ad, second ad is another creative. You want to see which creative more people like. So that once you have done the testing, you will have the winner is the ad that you want to continuously show, because that is giving you higher click rates. Now typically what happens is we have two tests A and B, two options going on, and A and B you run it, and whichever click rate is higher, we conclude that that is better. Can I really prove using a statistics?
P-value lower, which are having P-value lower.
But how do I get the p-value? Because you are running two tests and you get finally two values, click rate A or click rate B. There are two numbers. Now how do I test? Because to do all the testing I need standard deviation. So from where is my standard deviation going to come? From where is my standard deviation going to come? So in that case, we have to think innovative. What you can say, okay, my ad was running for 31 days in a month. More or less both the ads Google was showing more or less to equal proportion of people, because initially I did not bias it. I said randomly you keep showing it. So I'll say whatever the day 1 click rate, day 2 click rate, day 3. So I'll have 31 click rates for option A, 31 click rates for option B, right? Can I compute now mean of these 31 values? I can compute. Can I compute standard deviation of these 31 values? I can compute. These are two different samples. These are two different samples. Can I apply two sample t-test? I can apply two sample t-test and validate, is there sufficient, is there statistically significant difference in the click rates or not? Because mean, one fine day, probably I had got tremendous high click rate on one of the ad. Because of that, average of this and average of this came closer to each other. But that was only one fine day. But rest of the days, one ad was underperforming, that ad was underperforming. So to really prove, you require to be slightly innovative in getting the data. So that can be a way by which you can statistically prove offer A is significantly better than offer B, or offer B is significantly better than offer A. So you can go ahead and implement in your organization.